after the core program will be more or less completed, all problems which are interesting from all over the world, it is not the property of Russia and Spain. It is policy is quite open. A big part of the observational time will be in open access.
So what is the expected lifetime?
The lifetime guaranteed time 5, but we consider now that from the experience that 10-year lifetime is quite a good estimate.
Any other question? Okay, so let's thanks again to the speaker. Let's move to the next talk by Swarnakanti Ghosh. He will be talking about ultraviolet imaging telescope and the scientific results.
Нет, не сами там.
Good morning, and first of all I thank the organizers and also this forum, Russian Indian forum, and people here who are hosting this meeting and inviting me to give this talk. And primary purpose of this talk is more to further the possible collaborative programs with common science interest. And the last talk, Professor Shostak already kind of set the stage for where those collaborations could be, because he covered a lot of these science things. Okay, so I will be talking about this instrument which is recently in orbit, ultraviolet imaging telescope. As the name suggests, it's primarily imaging, though some little bit of low resolution spectroscopy is involved. So I have listed here the in order of importance the contributions toward this project. So our institution is here, and there is some Canadian contribution also. So I have planned my presentation in this way. I will give some details about the instrument itself, what we are seeing its performance in orbit, and a few science results which are just, it's not yet firm, but what are the kinds of science one is doing, and finally how one could use it further. Yeah. This is just to remind that we are talking about which wavelength range. So it sets the wavelength scale. So when we talk of far ultraviolet and near ultraviolet, of course last talk also mentioned these things. So not to be confused with also a U band which is possible from ground, which has also been important. And atomic physics wise these numbers are relevant, which tells about possible background one expects in low Earth orbit on Earth. So basically 1200, so Lyman alpha one has to avoid if the solar system generated background is to be avoided. So one has taken care of this while designing, and this is just to show why one needs to go to space. I think I don't need to tell this to this audience, but we are talking of only this minor place here in this log scale where entire electromagnetic spectrum where astronomy is done. Of course, balloon-borne things can be done. So this y-axis is where half the photons are still available to you at this linear scale height. This is log scale, extreme log scale. So basically, radio and optical is the only one where you can do extremely deep ground-based observation. Okay, so UVIT has the target of spatial resolution better than 1.8 arc seconds, and simultaneously seeing a roughly half-degree field in 3 broad channels, and in each of these channels one has sets of filters that is unique compared to galaxy what we heard earlier, and then there is a scope for slitless spectroscopy in UV. Actually, optical channel has been added to improve the pointing and to achieve this resolution. The spacecraft itself doesn't give the position, the aspect information that well. Okay, so this is just a schematic of the telescope. This is sunshade, these are baffles. So it's a primary mirror, secondary mirror. There's a hole in the primary through which radiation goes, and then the filter wheel, and where you select the filter, and then finally the detector. So it's a Cassegrain system. Many of you would be. So there are two telescopes, one dedicated to far ultraviolet alone. The other one has a beam splitter here. The reflected part goes to the near ultraviolet and the transmitted ones to the optical. Because additional aberrations come for this component, so that's how the reflected is taken for the UV. Okay, so what are the real competitor to this instrument? Of course, Hubble Space Telescope has been and will remain even now. But let's see in red. This is a busy slide. Please concentrate only on these numbers in red. So HST can, of course, some of these instruments are now retired, but okay, up to about 2.5 arc minute kind of the area could be imaged in using HST. Other things are even smaller. So simultaneous large angular resolution thing, HST was not the primary thing, but of course we know, given the pixels scale, to do very high resolution imaging, as well as there are many spectrometers which are there, but UVIT is no competitor for that kind of instrument. There has been few, as we heard earlier. Now Galaxy is the main competition, and so it has a 50 centimeter collecting area, but angular resolution is of the order of 4 to 5 arc seconds, and NUV has more or less done all sky except for some bright regions, and it also had low resolution spectroscopy. So I will just put the metrics of comparison between the two, Galaxy and UVIT. So Galaxy, so we have two telescopes. So this was very fast. So this is f12. So field of view stress, we have so main thing you see here are the filters. This was a fixed band, and we have selectable filters. And we are using grating for low resolution spectroscopy, whereas there was grism here. Resolution is similar. And for far ultraviolet, we have two of these gratings crossed at 90 degrees. For the same spacecraft roll angle, we can actually take two spectra without much overhead on spacecraft movement. Yeah. So this is the key factor actually, and we'll see the impact on science use of that. Effective area, which is kind of sensitivity, a factor of 2 down from Galaxy in far ultraviolet, slightly down from near ultraviolet, basically because it has a much bigger mirror in Galaxy. So this is the comparison. So this is wavelength versus effective area. So this entire thing is the far ultraviolet, and within that we have multiple filters in different colors here. So basically these are crystals which are pass band starts from certain wavelength. So as I said, this Lyman alpha would have a lot of background here, but if you take barium fluoride and this sapphire, so between these three filters, this one is very inefficient, but color in these filters will give additional information even if whatever Galaxy has already would have measured. And now similar thing for the NUV band, the Galaxy has this entire collecting photons all over this. So we have these different filters. Some are relatively narrower and smaller effective area. So particularly colors here again will give a new dimension to what Galaxy would have imagined in a single broadband. Okay, in optical also there are filters, but that's primarily used for tracking the space. So this is how the detector looks. So photons enter here, and then there is a microchannel plate, and so entire field of half degree is kind of reduced by optical reducer to condense the image onto a silicon CMOS device, which is read out fast as a photon counting system. This picture you saw just now, this is the back behind the mirrors, behind the focal plane volume. A lot of this tubing is to keep the contamination away, because dry nitrogen has to fill, because optics can get UV dead with a very tiny amount of contamination, and we have very little chance of checking the actual quality of how we have preserved, because it has taken several years to integrate and it has been in the lab. So there are various witness samples which are checked regularly to see that it is not dead, the detector is okay. So this is at the Thermovac in Bangalore, where Indian Space Research Organization carried out the various temperature tests, etc. This is the integrated thing. So these two telescopes are, these two are the UVIT, this is X-ray. So most of the other payloads are X-ray astronomy payloads, which are much heavier and primary, so UVIT tubes just before launch. Okay. So contamination has been a major issue, and we have, so UVIT door was opened on 30th November last year, so close to 1 year. First flight target was this star cluster, and performance verification phase went on for about 6 months, and then it was opened for guaranteed time, and Indian PI waste thing is opened this week, last week, 1st October 2016. Okay, some of the engineering things I will skip. So all that fear we had about contamination, we have now seen far ultraviolet sensitivity to be within 10% of the expected. So there has not been any major flaw. Okay, so this is the kind of FWHM we have achieved in NUV. So although target was less than 1.8, we have actually done better than that, looks like, and IFUV even slightly better. So this is to be compared with 4 to 6 arcsecond of galaxy for crowded field objects. So then in the performance verification phase, various filters have been calibrated, and so this one 0 point magnitude is basically, this is the AV magnitude for which 1 count per second translates to. So these are the numbers for galaxy, and these are our various filters. Yeah. Sky background. So main background is the zodiacal light, and then in NUV and in galactic background itself. So we have quantified from deep images of this particular galaxy that 26 magnitude for 10 square arc seconds solid angle, not per square arc second. So these will be the limiting things for doing very deep imaging. In far ultraviolet it is 25.5. Now, yeah, so there are these cosmic ray effects which we are seeing a lot, but then we have devised, so there is a long chain of data processing pipeline which aligns this photon counted images for the spacecraft drifts, as well as many calibratable systematic effects of the detector, optics, and various things which have been calibrated in lab over the years and verified. Some grid of points have been verified in orbit. So the software which does all those corrections can also identify and remove these cosmic ray events. So actually cosmic ray based this kind of things are not going to affect the deep imaging. So this is a typical raw image of a galaxy, and this one, and this is how it looks as the raw image what the instrument sends. And after you run that pipeline and correct for various systematics, this is how it will look. This is about 1500 seconds. This is in far ultraviolet. The graininess is because of the, of course, lesser number of photons in FUV, and this is the combined galaxy and UVIT for similar integration. Okay, so we have to exploit the angular resolution, and so basically image higher stellar density targets, and of course the multiple filters. So these are the two key takeaways. So projected science, of course, has been many things for when the proposal was written, but what one will be doing, of course, will depend on interest today. And okay, so this is that resolution of 100 slitless spectroscopy result. So this is a planetary nebula whose spectrum is raw spectrum is just displayed here. Okay, so these are some of the science images after collecting all, carrying out all the possible corrections, etc. So this is the cluster, and some of this is just a blown up view of some smaller part, and you can see one of the cluster galaxy details here. And in this cluster, if you compare all known galaxies in that cluster with known redshifts, that's in red, and the blue ones are the ones which we have definite detection in UVIT for whatever integration time that was. So this is redshift. So even at higher, so there is no bias of redshift as of now what we are seeing. So we are seeing quite a good fraction. There is no cutoff. Okay. this is one of the first, as I mentioned, the first slide when you open the door, we had looked at this open cluster. We wanted to just have a cluster which is filling up the field of view so that we can calibrate it well. So from that, we could discover a hot companion to a blue straggler. Serial number is basically this is the, so basically multiple filters of UVIT has been able to quantify and characterize that is the binary nature, though that there is this blue straggler is comprising of so basically breaking up. So by modeling, one could break into the cooler component, which is the blue straggler star, and the hotter one, which has been doing the mass transfer to the. So this is the first time this kind of a companion to a blue straggler has been found. So this is a comparison with a globular cluster. So this is a ACS HST Hubble Space Telescope image. These arrows mark the place where we are looking at. This is the UVIT image, and this is the corresponding field galaxy image. So we are almost seeing, so except for the very central region, maybe we will be able to do what HST was doing for slightly larger solid angle place, and obviously much better than the galaxy. This is a typical example. It is telling, but it is just that it's a comparison from known model of that to what is the measured curve. So these are using the filters from UVIT itself. So there is something to learn here, that what has to be correct, means what new information in the modeling about the known cluster one could do. So basically it's a color magnitude diagram using only UVIT data. Okay, so now changing the subject now. So this is the kind of science programs people have been doing using galaxy images and 21 centimeters. So here I propose that using GMRT and UVIT, one could take up much more better angular resolution challenging kind of projects, where you can have a sub arc second level 21 centimeter image as well as 1 arc second to 1.5 arc second level UV image in different filters also, and one could. So Galaxy has, as the last talk also mentioned, a lot of these extended UV discs have been seen. So Galaxy has done a lot of those, and one can now further resolve those or similar kind of things. Okay, so this one quantifies what all. So guaranteed phase. So launch was September end. So first 6 months was performance verification, and then next 6 months was guaranteed time. In that we had some share, and first year, which began 1st October. So proposals can have any kind of OIs, but PI decides which are the reserved times. So any Indian can now onwards start using it, grows with time. International PI will start October 1st, 2017, 10,000. Then onwards it will remain 10%, and then onwards 20%. In next years will be similar. So this was to just motivate the possible interaction between Russian and Indian scientists from their own kind of science problems which they have been already pursuing, or think of new ones. So I think I'll stop here.
Thank you. So time for questions.
But it's not question first. First, let me congratulate Indian colleagues with this success, because I know what life is.
Yes.
Yes, and life is not easy.
It
But
has been many years.
eventually, yes, he got this instrument in space, and I wish, of course, the further success for you. Now the technical question.
Yes.
That you use the MCP detectors, I believe.
Yes.
Otherwise, you couldn't have this timing with no CCDs,
Yes.
I guess. You will be limited in observation of bright sources, because you know.
Yes, actually that has been a major problem, because so onboard hardware has a safety by itself, it shuts down, because It can burn the detector if there is a too bright a source.
You have great filter of how prevent the exhaustion of the...
No, so what we do is there is this, so we have photocathode, which is generating the first photo from the UV astronomy or background photon. So then the MCPs have these high voltages going up to 8000 volts in a few millimeters. So that multiplied thing then hits a phosphor, which is the anode. So the light will splash. So it's a photon counting. So each entry photon leads to millions of electrons at the end of the MCP, which hit the phosphor, which makes a big blob of light. So that
you explained the technology of working of the
Yes.
MCP detector.
Yeah.
I just say that the MCP detector couldn't be used for observation of bright sources. By us, we are thinking about to introduce
So I was coming to that.
filter too.
Yeah, so I was coming to that. So this high voltage is what we have done is, we have always imaging, we start with a ramp of the high voltage. We allow a few seconds for the high voltage to settle, and that time the image processing onboard in FPGA code is trying to judge whether it is safe field or not. If it is not, it shuts down the imaging process and tells the spacecraft to shut down the other two channels also. It could happen to either. So that's the onboard thing. But proposal itself, when it is submitted, we have a scheme that you have to first justify technically that it is a safe field using catalogs, known things of that field. So we have multi-level safety.
Sorry, that's right.
Thank you for your comments, and we look forward to the kind of science you talked about.
We'll
It's
get
possible,
back.
yes.
I'm eager to contact.
Yes.
Sorry, I missed it from your talk. Do you have any observations? And the second question is, what will be the data availability policy?
Yeah. So first thing, so originally when the proposal was written, we wanted to do a survey, but given the Galax things already, and we know that instead of doing a very large solid angle survey, it is better to pick the solid angles you want to do, because already you know NUV image in a broadband how it looks. So I think the science return will be better optimized by using the available data instead of doing a blind survey. We are planning for very deep survey of some selected fields to go to as deep as possible. And sorry, your second question was about the data. So all the observations are lock-in period is 18 months. Actually, there is some discussion, maybe it will be brought to 12 months. Only guaranteed time, performance verification phase, engineering data will not be public because it's not very interesting to normal scientific community, because there are too many things have been changed which are not the released modes of observation. The instrument has many more capabilities than what on the web page tells how you can do the imaging. But any proposal, PI has the thing for 12 months.
We have this information. What is the field of view?
28 arc minutes, roughly half degree dia. And Galax was 1.2 degrees. That's the major difference.
It's very interesting, really. All this.
And it is designed for 5-year life, but we expect, like you said, beyond. Of course, 1 year is over.
Have you published some press releases now? Because it's this information I see it for the first time.
Yeah, so
such a
there has been
detail.
some local press we have done, but we are waiting for some of the things to, some results are in journal offices. So once the acceptance from the journal comes, we will be going in there.
SPI proceedings.
Yeah, of course it has been in SPI proceeding, etc. Online instrument details are there. Many of the tables I showed, those are all there, public. And yeah. So we are expecting in few weeks some of the things to be in there.
technical, but this first images, it's
Yeah.
quite fresh.
Some of them are in
It's
journals.
just very
Yes, submitted to journals, but some are within the group. What more science can be brought out of that? So actual performance related thing will happen very soon. But key science from that image. See, right now what results I showed were not planned as science. They were planned to characterize the instrument.
Yes.
So actual things, those observations were made more recently. The ones where there was a peer-reviewed proposal. PV phase observations were done by the instrument team itself. That okay, what do you want to demonstrate the capability? From that phase, not from the key thing. So that would anyway, the rights would be with the PI of the proposal in any case. Yeah, so guaranteed time, like Devendra and I, we have been doing some galactic structure study plus because different filters compared to galaxy has other kind of possibilities and some face-on galaxy imaging.
How big is the community of Indian users of this instrument? What is your estimate?
Yeah, I don't know. It's a small community, but we are trying to multiply using a lot of postdoctoral and PhD students as many. So we have been, so there is a different arm within Indian community which is holding regular meetings at different cities of India to get excited. But I would put maybe active researchers, maybe 30 to 50. And that's basically these are all multi-wavelength. It's not particularly UV. There is not real UV astronomer. They are all astrophysicists who get information from any wavelength that helps that science.
So AstroSat had X-ray, 3 X-ray instruments.
Not Indian.
No, that will, so many of these proposals have non-Indian COIs. So foreign COIs will begin from 1st October 2017, as I showed. 10% is only for that kind. But even today, anybody can be COI. It's only PI identified. Like guaranteed time also, instrument team member has to be PI, that's all. But the collaborating team during the proposal itself or during the analysis or during the interpretation of the observation. So welcome collaboration.
Okay, so let's thanks again to the speaker. Let's move to the next talk by Andrei Sobolev. We'll be talking about gravity of feedback mechanism and formation of stellar clusters in giant star forming complex D174.
Just shift back to radioastronomy.
Пожалуйста, поближе к доске и поближе к камере.
А вот если можно, с той стороны.
Так что предыдущий докладчик.
С другой стороны.
Ну вот так вот.
А это листает?
Листает, а только подключить правильно.
Вчера не стало. Okay, so I will start a bit. My talk is called Variety of Feedback Mechanisms. What does this mean, in fact? The feedback mechanism is that the stars are formed, and after that they influence the medium surrounding this. So this comes in very many varieties, and it lasts for very many years. For example, there are some immediate things like Professor Oja talked about is the outflows and something like this. This is a feedback. So if it is a accretion disk, so this is influence of the surrounding matter on the stellar object, but outflow is a feedback. And another thing is for example, the expansion of H2 regions, which is also was also mentioned here. This is quite large-scale event, and it changes the surrounding medium, ionizes it. There are shocks going, and so on. So this is also very important phenomenon. But if the outflows, even the low mass stars can influence the medium in this way. So the expansion of H2 region is possible only in the case of the high mass star, because the low mass star cannot ionize the surrounding medium. Then the other type of feedback is something like supernova explosion. That means that this is one major event which is very large scale and influences the whole region, the whole star forming region, not only its small part, and it lasts for quite many years. And also one can understand that these feedback mechanisms, they are not, how to say, not constrained only by the outflows, by the radiated things and some shock waves. They also can be related to formation of big star clusters, which are, by the joint effect, can modify the regions around them. For example, all of us know that if we are forming a stellar cluster and it is formed from some parent material, at some point this material is dispersed in some way. This is a less studied phenomenon of feedback, because no one really knows how this is going on by the tidal effects or something like this, but that's it. And then, if we're coming further, so we have a collection of clusters. So this collection of clusters also can affect the things like, for example, this is a propagation of the spiral density wave, something like this. This is also kind of feedback mechanism, but of very large scale. And all of these feedback mechanisms have a lot of their subtleties in how they are working and how they are changing the matter around them. First of all, for example, we know that the turbulence does exist in the interstellar medium, and it is well measured, but how it is introduced there is still a question. One of this is just input of the energy and of momentum through the outflows, through collective outflows from the stars, individual stars and stellar clusters. Then it's but this has a lot of varieties, because these outflows are sometimes they are collimating, and sometimes they are quite wide field, wide angle, and so the influence of these outflows is very different. So if we are looking, considering the possibilities of how the expanding H2 region are changing the matter around them, it's so this also goes in very, very different ways. One of them is that for example, expanding H2 region, if the matter more or less uniform or doesn't have very sharp gradients, so it collects the matter, and then this matter is fragmenting and forming stars and so on. But another story is when the expanding H2 region needs some pre-existing clumps of filaments, and it's another story. So, since this conference is called Radioastronomy and Star Formation, so one of the most interesting things is how this feedback influence the matter and how to say, trigger star formation or initiate and star formation processes or quench them or something like this. And in my talk, I just wanted to follow all these things, starting from the very large scales to much smaller scales.
Я думаю, что лучше, чтобы не мучить Андрея. Ты угодно сказал, как если вы не
Я не собирался это угодно говорить, правда?
Okay, so maybe this technical problem.
No,
Let's
it
have
doesn't matter.
concentrate now.
Of course, because you have
Трансляция все идет.
Трансляция идет.
Тут, короче, техника не хочет с нами дружить, поэтому мы сделали перекур, так что такие дела.
Переводчики.
что
What do you want?
you stop there.
Как отсюда заметить?
Ну,
He will talk, like right now he's talking solo, because he's not here. Difference next of the after this. So,
Так, это у нас... А, так она есть, эта презентация.
Она в PDF. Ей надо перевести.
this is PPT file, so. Thank you.
You will use the PDF, yeah?
Для меня ничего зависит. Сейчас, по-моему, будет все собрано.
Ну да, видимо, да. Как логично немножко.
Начало, наверное, успеете посетить.
У нас изменилось расписание, да?
И чего это, когда меня...
Вдовина нет.
Вдовина, он так это, отказался?
То есть у нас сейчас Соболев, потом...
Как вот все идет дальше? Я самый последний, поэтому я как бы не волнуюсь. То есть если только меня вот сейчас их поставят, я буду... Устройство, да. Так, документ. Да, Астра. Вот Russian Indian. Вот и здесь должен быть репорт, вот этот этот PowerPoint-овский. Репорт, нет, репорт. Вот. Ага. Может все переименовать в Пирогов там?
А я сейчас переименую,
да. Сейчас. И попробовать можно там, если уж. Да, есть. Что-то есть. Да.
Но листайте довольно долго. Дальше. Сильно дальше. Идти в конце.
Ну что-то не может такие.
Здесь вот по-русски я его перевел.
Ай-яй-яй-яй-яй-яй.
Ничего страшного. Да, почти. Вот здесь. Вот, все, уезжай. Видишь? Можно полтела.
Там никаких прямых нет, ни анимации, ничего, поэтому все равно. Там
сейчас...
Петр Михайлович, мы нуждаемся еще в нормальном аппарате, чтобы заехать потому что у нас нет, я могу взять.
कुछ इसकी कमिटी हुआ उनका
Ну, я так один раз испортила флешку.
Даже когда мы ее пишем, она
Ну, вот как
она почему-то не знает, с каких форматов. Там ничего не было. Не, главное, чтобы она здесь поднималась.
Так, шутка, я могу удалять.
Вот их, по-моему, вот он меряет. Реально меряет. Ну вот освещенность. На открытой диафрагме можно ну, по мне, это артикулятор обычно, там же не видно, что специально выбрана шкала диафрагма выстроена таким образом, чтобы они не менялись по логике. Видишь, что ты берешь, смотришь, каждое деление, оно соответствующее, оно не меняется, могут увеличиться. И, соответственно, а видишь, линия, получается, что шкала выравнивается одна относительно другого, точно верьте важно. А это получается. Там приводчики. Приводчики. Вот. Да. Соответственно, получается, что если, соответственно, набор диафрагмы, набор выдержки. То есть можно высоко поставить, условно говоря, на диафрагму. Old school. Это. А тут все профиты закрыты, да? Ну, не все. Ну, не все. А что надо? У меня надо выйти на сайт через 777. проще всего взять чей-нибудь мобильник и с него вылезти. Возможно, и телефон. Им закрыт, скорее всего. То есть какие-то пока открыты, какие-то закрыты. Вообще довольно видно закрыто.
Хоть когда-то нормальные яблоки боишься. Ты куда? Вернись. Немедленно вернись.
Наладили? Ой, зенит прикольно, что ты кинопленку снимаешь одну. Какой? Зенит ТТ? Классно. Дима вот взял свои зениты. На черно-белое? Цветной?
Не, мы уже не сами здесь.
К зениту?
Да. Ты просто по нашей представить там. Ты можешь по НГУ скажу, у нас тут НГУ, собственно, Майя, Шалина, практически. Доклады здесь по одной информации, поэтому они нам все говорили, что делать, первый раз вообще слышал, мне сказали об этом бабушке, да. Сверху, и вот сверху, ну ладно, давайте. Ну, сейчас заполнить. Никак не заполнить, не заполнить, неправильно заполнить. Как правильно? Вот так. Заполнили правильно. А вы знаете, что несколько карт еще аннотацию, еще вариантов подписи. Хорошо. А раньше почему вам говорили? Мы не говорили. Это мы вам говорили. Ладно. Кто делает? Далее. Вот эти документы. Скажу. Причем потом сказали, через других людей, что мол, они уже давно отрезали, и все доклады. Зачем погонять их? Времени. Эксперт, вообще сам эксперт, ну, здесь специально занимается расследованием. Документ сдался, подпись эксперта, тогда они берут, начинают сравнивать. Соответственно, название сдался, данные, причем они типа на грубо говоря, точка не так стоит, слово не то, короче, у вас тут абзац не столь, короче, пунктик иначе, делаю, даже 50 раз, здесь вообще это пароль, да? Я живу
Что, мы, видимо, начинаем, да?
Где вот этот канал? Нет, кстати, я хочу проверить.
Работает?
Работает.
Что память не жалеет? Я чуть стриму запустил. Память все нормально.
Трансляция работает.
Just once.
Okay, so let's restart again from by please.
Okay, so the feedback mechanisms were started in this region, which contains as a part famous star-forming complex S231, S235. So it was started by many researchers in different countries. For example, here we see that one of the first studies of feedback mechanisms of the outflow type, which is done by Marcello Felli and others in S235 ABC. So I will not mention all these things. I will talk about some different things. So in Germany, Hendrik Borte seen a lot of outflows coming from one stellar cluster and so on. So there were in the other places these small and tiny outflows were studied by Shepard and Watson. She was working in Chile, so it's shown this way. So the distance, at present we know very well the distance to this complex, which was measured by trigonometric parallax method by Ross Burns while he was working in Japan. So many instruments were involved in this study. But first of all, whether some molecular complex does exist, it's normally a good question. What is the size where there is really outline of some giant molecular cloud? So can we make some border? So this is the end of molecular cloud, that's its border. So in the case of G174, this is quite well defined, good how to say, site where the gas is located. So this shows you a galactic plane. It's 10 by 15 degrees in galactic plane. Here is galactic plane. Here is the scale. It's 200 parsec at 2 kiloparsec distance. So this complex, this molecular cloud has size of about 100 parsec. And this square is inclined to show that this is the direction of right ascension of declination. These are galactic coordinates, and these are this shows you the directions of equatorial coordinates. So this complex was very well and with a much higher angular resolution mapped, for example, with SMT at Arizona, and here we see the map of this cloud, and we see that it has a lot more structure than what was known before. This is the paper of this year. It's 2016 September, so last month. And this is the complex which I told you, which is part of it. And this is S231, S235. This is S231 region. This is S233, S235, S232, and S234 is quite far away. I don't know why. So if we look at the map of distribution of the CO and H1 in our galaxy, so this is our galactic plane. So we see that this region is situated 2.5 degrees above the galactic plane. And but anyhow, it's quite well pronounced both in atomic line, in atomic hydrogen, in continuum, in CO, and in the infrared. But we see that this region is quite isolated from the others. It's not like a mass in the galactic center. So here we can really study mechanisms and the objects in more or less pure case. And we can expect that this is the simplest case. We will see the simplest case is very complicated. Okay, if we look at the position of this complex in the 34.5 megahertz, we will see almost no emission from this region. But if we come into higher frequencies, we immediately notice that there is something. But at the same time, we immediately see some hint that this complex is part of some much more huge formation, much bigger structure. And if we that this the outline of this structure. Okay, so going higher and higher, we see it's more and more pronounced. And this is 21 centimeter, and we really see that this is a quite bigger structure, and it has a waist. Just here is galactic plane. Yeah, so here is some bubble, and here is some bubble, but they are connected to each other. Whether this complex is part of all this structure, this is one of the things which I would like to discuss. But one thing is immediately understood, that this huge complex has no relation to the spiral arm or something like this. So this thing is formed by some local, very large scale, 100 parsec scale, but by local phenomena. And we see the major things which are taking place not in the galactic plane, but about 100 parsec above and below galactic plane. And if we look at the ionized H2 regions, which I told you already provide a lot of feedback, we see a lot of them, and but here is a good concentration of them. You see, they are well pronounced at 21 centimeter, so they are also pronounced at 11 centimeter. A bit less pronounced, but we really see the big structure and the H2 regions here. And they are also quite well seen in H alpha emission. So we also see this structure in H alpha, and even its waist is pronounced. Further, so these are H2 regions. This region contains open clusters. That's very important. That's very interesting, because in this way we can study star formation history. Whether this thing is related to star formation, whether there is ongoing star formation there or not, but we see that in our major region, which we are going to explore, there are no existing open clusters. And of course, if we have open clusters, we have very interesting things to do with them. We can determine the distance, we can determine the age, and other things. But in this case, these determinations are quite controversial. But anyhow, so we see that the youngest clusters here are the embedded. So we see some gradient of the age in this direction. Yeah. But you see that in any case, here we have 10 to the 9th. So age of these clusters are 10 to the 9th. If we believe this, it's very interesting. How can such a big structure survive for 10 to the 9th years? Yeah? But anyhow, it does exist. If we look at, there are some other open clusters here. They don't show anything very prominent or important, but I would like to draw attention that studies of open clusters in this region and its surroundings can provide us with understanding of what's going on in this part of our galaxy, which is associated with the Perseus arm, but it's quite interesting. Anyhow, see, if we think that there is a gradient, so this is the youngest part, this is the oldest part of this structure. This structure does exist. It's quite well seen in 21 centimeter. I've shown you, but it is also quite well seen in polarization. So polarization in this case, you have to understand. So here the big structures which we see in polarization, and here all of them become very small scale. That means that this is H2 region, this is ionized hydrogen, which depolarizes the things. So we see this structure in polarization. Okay, so now let's come back to molecular gas and to the star formation and feedback mechanisms. One of the things is that if we look at this structure, we see that there are some CO emitters even in this place and so on. So many of them are associated with the iris sources, and this region was traced or surveyed by a famous group, this Waterloo and Brandt. So they determined the velocities of CO, and we see that velocities of CO, they have quite clear gradient from being the bluest in the north to the reddest in the south. But mainly this comes from 0 to 20 kilometers per second, so the gradient is not that big, but it does exist, and it is clearly pronounced. So one of the things which is really interesting, and which was reported by Kunk, Koh, and Salter, is existence of the supernova remnant here, which is traced by atomic gas, by H1 emission. Though it is called an old supernova remnant, this supernova remnant is something like 0.3 million years. So it's very, very young in comparison to the open clusters of 10 to the 9th, which do exist in this region. And whether this supernova remnant can really determine existence of this big structure and its functionality, it's a big question. Another thing is very important and interesting, that the most pronounced H1 emission in this supernova remnant has velocities of 30 to 40 kilometers per second, while I have shown you that molecular gas has velocities from 0 to minus 20. So they differ from each other by velocities to quite great extent. But at the same time, this shows you the contour maps. This is red is quite funny presentation, not channel map, but so red here in this figure is emission from 35, integrated emission from 35 to 45 kilometers per second, green from 25 to 35, and blue from plus 20 to plus 25. Yeah, we see, and these contours are 11 centimeter emission continuum. Yeah, we see that they match each other more or less, but here in the grayscale, we see some emission which was from minus 28 to minus 25 kilometers per second. And we also see that there is also blue shifted and red shifted emission. So the difference in velocities is quite high. So, and we see that maybe there's a joint effect, not only one supernova explosion, but several of them have taken place in this region. One of the things which I wanted to show is that this is so-called emission, they call, but in fact it is superposed and much brighter background emission. And this, in the case of one line, it's very difficult to disentangle the question when we don't know what exactly is the background emission, because you shift and again you have superposition of the emission from this region and from some background. Okay, so coming to molecular gas, we see that, so this is global kinematics. It shows you that the velocities of molecular gas, there are no molecular gas at the positive velocities. They are around minus 17 kilometers per second and so on. And the gas is quite broad velocity dispersion from around 3 to 5 kilometers per second. So that's it. And now let's come to this S231 and S235 complex, which is a general part of this region. And what do we see in this case? First of all, we see H2 regions in H-alpha emission. Yeah? What does that mean? This means that they are situated on our side of molecular cloud, not on the back side. If you look at the supernova remnant, you will immediately understand that if it influences this region, it hits it from the back, while we see H2 region on our side. Yeah? One of the things is that these stars may come from some place and we don't know from where. And in order to understand where these stars are coming from, we just measured the velocities using 6-meter telescope, big telescope azimuth of this Special Astrophysical Observatory of Russian Academy of Sciences, determined the velocities using very high spectral resolution. And we have seen, so these are heliocentric velocities. These are not local standard of rest, so different from each other. But you see that these velocities, they're quite well matched velocities of the gas, except for this star, this ionizing this H2 region. But this is a binary star. We made its study, and we have found that its barycenter is also moving at around -19 kilometers per second. So all of these stars have the same velocities as molecular gas, and so they are born in this place. Yeah. So there was some big and unknown mechanism which have driven all this gas from our side to the back side. Yeah, and we don't know what's that. Another possibility is that they were formed at the edge of molecular cloud or molecular layer. So they paved their way in this direction, but didn't do this in another direction. This is another hypothesis, but anyhow, all this tells us that since all these stars are on our side, and there are no ionizing stars on the other side, yeah? So that means that some very large-scale phenomenon had to trigger formation of massive stars on one side of molecular layer. This is something interesting, and this resembles some feedback of very large scale, which I mentioned already in my previous talk before the coffee break. So all this resembles us the modern paradigm that to form molecular gas we need several multiple episodes of compression. So we see that the supernova were hitting this gas from one side, another event was hitting it from this side, and there were some other large-scale or maybe supernova explosion or large-scale events which were influencing this gas very long ago. So some maybe billion years or half a billion or parts of billion years, not millions. And these layers are forming, and then you have this big star forming complex. So you see, that's really very interesting. So we don't know, but some large scale things were producing feedback which produced star formation. So, okay, so these are just details. But further, if we look into this molecular cloud, this is an old map by Haier, or this is the region, and so these are channel maps, and we see at one place here, we see that quite distinguished and emission which is not that diffuse. It's in fact is some gas which was entrained in motion by expansion of this H2 region. So we see another type of feedback mechanism. So the star was formed, so there was expanding H2 region which entrained gas in motion. So it moved it. And another thing is that tells you about some difficult things, that we really see a clear gradient of velocity. So more positive velocities are to the south, and more, how to say, negative blue shifted velocities are in this direction. So there is a ground, the whole star forming region is rotating or it has quite a strong velocity gradient. So it's also fashionable now to explain that the rich stellar clusters are formed due collisions of two molecular clouds, and we can imagine that there are two interacting molecular clouds here. So what's about molecular and atomic gas? They are situated in this way here, and if we look at so grayscale is atomic gas, and this is CS emission, which was mapped by us. And you see here, this is S235 region, that at some velocities we really have lack of atomic emission at 21 centimeter, and at the same position at the other velocities we see quite pronounced enhancement. This is a background emission, which was just not integrated but averaged in the big field. So this is emission toward S235 region, where we saw this lack and enhancement, and this is a subtraction, and in fact we have something like this. Yeah. So here is absorption, here is emission, and so due to this we can determine that here the excitation temperature of gas is lower than background, and here it is higher than background, so we can determine the excitation temperature of atomic gas here, which is quite interesting and funny. And another thing, so this is one part of expanding H2 region, this is another one, so we can determine the velocity of the center of this H2 region and the velocities of these things, so we can determine expansion of molecular, of atomic gas. Sorry, this is in Russian, but you see that the expansion velocity is about 7 kilometers per second, while the H2 region moves it with minus 17 kilometers per second, which is quite well consistent with the velocity of the star and velocity of the and velocity of molecular gas. We also have here radio recombination line data, which shows you that yes, okay, we have just this thing that first the radio recombination lines, ionized gas moves with the speed which is higher than the speed of atomic gas and the speed of molecular gas. So there is expansion and at the same time contraction. So that's how the feedback goes. Okay, and this is interesting thing. This shows you the extinction from two mass star counts, and this is distribution of molecular gas. So they match each other. That means that we really have some complex in which the dust and gas distribute almost correlated with each other, and the star formation is going on. We have analyzed the filamentary structure. We see quite clearly that it's a lot of filaments, and in fact the brightest stellar clusters are produced on the intersection of these filaments. But these filaments have a characteristic size of 4 parsec, not 0.1, which is stated by Philippe André and others. This is 4 parsec. This is much more bigger filaments, which contain a lot of threads and so on. This is also these AV estimates, but using UKIDS data, which provides you with possibility to make to obtain resolution of 1.1 arc minute, and this is called photon pattern distribution function (PDF). It should be really log normal in the case if we have turbulence here, but here it's greatly different. Log normal should go this way. So this is a difference. So this shows you that this region is not fully controlled by the turbulence. It is greatly controlled by the large scale feedback mechanisms like expansion of H2 regions and maybe some other things. So this is the study of what the influence of the H2 region, expanding H2 region on surrounding material, and relation of the gas here, we see dense gas, which is very well associated with the stellar clusters. And there we used ammonia to determine the parameters, temperature, density, and other things. So we can really see that there are some feedback mechanism, and expansion of H2 region drives the medium, which comes out of the difference in velocities of 13CO and CS lines. And we see here the gas which is influenced by H2 region and which is not. In the other younger and smaller H2 region, in fact, the star, the central star, has the age of about 1 million years, 2 million years. But we see that there are some blobs. We see this infrared and in reflection even, and these blobs they contain some additional clumps. So we really see some molecular material is driven or trained in motion by expansion of very young H2 region, and triggers star formation. This is the very initial stages, which is quite very rare to find the case, but we see it here. So these are the stellar clusters, a lot of outflows. That's what I told you. These are also some different traces of star formation activity. These are methanol masers of first class. The second, so existence of H2 region, the outflows, water masers and star counts show you that main star formation activity is located here. But in fact, if you look at this is S235, only this is what I have shown you before. But in the other places, we also have a lot of star formation activity. We see ridges and other things, and we have found that these things, they contain dense molecular gas. They display methanol maser emission, which shows that there are outflows, and a lot of these things are not studied at all. So no one paid attention to this. So there are several places where for very how to say, vivid star formation activity, which were found by my PhD student. Thanks a lot.
Thank you very much. Questions? So I have a question about these filaments, which you are talking about, CO filaments of width of around 4 parsec. But generally these filaments of 0.1 or 0.2 parsec are seen in Herschel, like far infrared. So you are talking about the same filaments? Or?
I'm talking about different. I believe that they're different, yeah. Because in fact, what is stated there. So at present, about filaments, what Philippe André discovered with Herschel, these are filaments of in the low mass star formations. Yeah? So in the high mass star formation region, they can be different. Though last year they observed in NGC 6334 and the same width, but there is a filament, but there is no pronounced high mass star activity there. Yeah. So that's it. Another story that at the intersections of these filaments, we see several stars are forming. Several. It means that 2, 3, maybe 5 at most. But in our case of our clusters, we have hundreds of members, or even thousands, because we don't detect all them. What produces these rich clusters is another thing. There should be a lot of filaments, but whether these individual filaments are forming something which is bigger, that's a question. You know that even 0.1 parsec filament, it contains, like Alvaro Arcad have shown, it contains some threads in it. So these filaments also can form threads and can form much bigger size filaments. That's what I'm saying. So there is hierarchical structure, and to form a very rich cluster, you need intersection of these organized structures of filaments.
On one of your view graphs, I could see the statement that multiple collisions of supernova Random-driven medium
Let it be.
Let's wait for the question. Let's produce magnetized giant molecular clouds. My question is, why it is stressed magnetized? Because I see that to produce molecular cloud is possible, but to stress magnetized, what is the reason? Yes, magnetized.
This is a question to Inutska.
But you should
but in fact, yeah, of course.
Why magnetized here? That's important. It is stressed.
It's
because to make orientation, to make these filaments, to start star formation activity, you have some way to arrange the things. Yes. First of all, one of the biggest questions. Yes, we know that the filaments do exist. How they are formed, due to which processes they are formed. Yeah, and the question, the main thing is just to form a filament, you need magnetic field.
It is not an answer, of course.
It's because they are talking about the turbulences there.
Yeah, he's talking about everything.
And Andrei, what main, how to say, novelties, what main statements you could make from this? We know that all the interstellar medium, especially in the giant molecular clouds, is very, very complex, a lot of processes, and so you have demonstrated in one concrete case in one region that there are several, but what is new?
I was talking about variety, and I have shown you that there are feedback mechanisms not only over small scales like the outflows, but also big ones. And so there are multiple episodes.
Okay, it is an illustration for the more or less accepted idea that multiple, that some various mechanisms, they produce this complex process of star formation. Yes, it is an illustration.
It's a kind of. The thing is that I was talking by Inutska-san, so I have seen this much before it was published, because we are talking to him. He said, I'm a theoretician. Please tell me something. I tell that in this case, the theory and observations, they come together. They match each other. Yeah? And we see that this variety of feedback mechanisms, it quite well fits to our current paradigm of star formation. But this paradigm is quite different from what we were thinking about even 10 years ago.
Oh.
Yeah? Yes. This tells you the existence of some quite thin molecular layer. So the star forming region, yeah, is not a ball. It is some layer. And this layer is constructed by some hierarchical filaments, yeah, which were also changed by expansion of H2 regions, and which were created by very large scale events with the time scales of about comparable, less but comparable to billion years. Yeah. So in this case, what is saying that's not something which comes from the ball. So ball is fragmenting, then the other parts are fragmenting, and so on. No, this is layer. These are filaments. These are clusters which are formed in the intersections of structures of the filaments. And there are other small scale clusters or low mass stars which are distributed all over the region. Yeah, and they also quite considerable part of them are formed not in the clusters but quite dispersed.
I consider your work here as an illustration of the
modern paradigm of star
formation with layers and so on. And the last question, maybe you mentioned the very old cluster, billion-year-old. What is it?
That's what I said. That's a question to the people who are working on stellar clusters, whether this is reliable or not.
Next talk you'll go stellar clusters.
Yeah, that's what I'm saying. So these are stellar clusters, but we have to pay attention that the stellar clusters, in this case, they can tell you the story of existence of a big structure.
It is very old. Because that's one
I-
million
it's,
years, that's a huge.
Quite, I know this, but
The star forming region, they never live for such a long time.
but this is not a star forming region.
No,
This is a big structure, but this structure, it contains star forming region at its age.
It's occasionally, I believe.
I don't know. Because we also here have this activity, and we have molecular gas on the layers and atomic gas. So this is a quite big structure which produces. I don't know, maybe it didn't reach this place. So this place was reached earlier, this is later, but this shows you a gradient. So I have shown you just the gradient.
We will discuss in that, right? Okay, so let's thanks again to Andre. Our next talk is by Yogesh Joshi. So he will talk about investigation of clusters to probe the galactic structure.
Thank you. My talk is on investigation of open cluster probe the galactic structure in the solar level. Though this conference is mainly on the radio astronomy star formation, and I'm observational guy work basically on observational astronomy. But this is the project which we have taken with our Russian collaborator to study the galactic structure using the archival data on open star cluster. Though we have also observed some of the open star cluster, but we have not analyzed them as yet. And so far in this project, we are working on the archival data of the star cluster, and even in my next talk after this, Andre will also tell about the archival data on the open star cluster, and he will further explain about the project. So this talk is basically our statistical study of the open star cluster found in our galaxy. A typical view of the Milky Way galaxy is this, and all of you are familiar here. And this is the Phaeton, this is the Phaeton view, and our location is this. And it is about 8 kiloparsec from the center. And if you see this star cluster, this is the group of stars, as you can see here. These are the group of stars, and which you can see in the sky, and you have to make sure that they are one entity. They are not just a field star or group of field star. So we have these star clusters which are physically related group of stars. They are held by mutual attraction, and they have roughly the same age, distance, and chemical composition. There are two types of star cluster, one is open star cluster, and which are basically formed star within the disk of the galaxy, and having some few hundred to thousands of stars, and often some millennia to billion-year old, and they are irregular shape, and nebulously seen to the dust and gas there. And then you have the globular cluster, which are quite old, and they are very concentrated cluster of stars, and mostly in the galactic. These open star clusters are very important to understand the galactic structure, in the sense that if you observe these star clusters at different parts of the galaxy, then as these star clusters have different ages and different chemical compositions at different distance and different part of the galaxy, you can use them to understand the galactic structure. And what we did with the open star cluster, and these open star clusters are distributed throughout the galactic disk and span in wide range in age. So they are ideal objects for dynamic evolution of the galactic disk to understand this dynamic evolution. And the open star cluster, in some of the open star cluster, not many, maybe I think 10%, we have the metallicity information also. And because these star clusters are observed at different part of the galaxy, so using those star clusters for which we have the metallicity information, we can actually study the chemical evolution of the galactic disk. So these are the advantage we have with the open star cluster. But in detection of the open star cluster, there are many constraints. That's why we still have only the 1% of the total star cluster sample, which we expect we should have. So it is the red lineage in the line of sight is one region which hinders the detection of many star clusters. And of course, the distance clusters are less luminous, so they are poorly observable. And then if you have the OB stars, they are visible, but the embedded region in the dust and gas, which again hampers their detection, and many are difficult to observe short away. And cluster too close to the sun, because there are many clusters in nearby region also, but they have wide angle of view. So these kind of clusters are also difficult to detect due to their sparseness. So cluster detection rate also depends on several factors, as number of stars, how many stars are there in that cluster. If there are very few stars, and it is again difficult. There are of course size also, angular size of the star cluster is important to detect it. Then of course distance and what kind of stellar background. If the stellar background is quite high, then it is very difficult to identify the star cluster. And of course your limit of the telescope, detection limit of the telescope is the other factor. There were many catalog of the star cluster produced in the archive. It was started from 1982 by Linda. Later, Webda catalog came out, and then Dice catalog in 2002. Basically, Dice catalog was a compilation of all the clusters reported by different groups, different scientists. And recently, the MWSC catalog, Milky Way survey catalog by Kharchenko et al. Group, they have produced this catalog, and in fact they have updated it twice. So they provide more than 3,000 open star clusters in the Milky Way, and the best advantage of this catalog, as in comparison of Dice catalog, which compiles the list of clusters from different surveys, from different papers, they have detected all these star clusters in a single pipeline using the data, and so this data is homogeneous in nature. To study the galaxy as a whole, we need a complete sample of open clusters. But as I said, there are very few number of star clusters detected. More than 3,000 is nothing, because we expect to have, theoretically, it is expected to have more than 100,000 star clusters in the galaxy. So this number is very small. And more than that, not just this 3,000 open cluster, but if you see the, their number density diagram, you will realize that this sample is even not complete up to a large distance. We analyzed the MWSC catalog, and we found that this catalog is almost complete up to 1.8 kiloparsec region. So this is the sample of the number of cluster in that 1.8 kiloparsec. If you see the young cluster and intermediate age cluster and old age cluster, so you can see that most of them are intermediate. When I say the young age cluster, it is less than 20 million years, and then and when I say the old age cluster, it is above 700 million year old. So in between there are the young intermediate clusters, and you see there are very few old cluster in the immediate solar neighborhood. As you can see, just a small number, most, and while if you go far off, you have a large number of star clusters. So this is the typical number density of the star cluster. I will talk about this in next slide. Why there are less number of old cluster. So the spatial distribution of the star cluster, you see that most of the star cluster, as we are discussing, are in the very close by of the sun, very in the solar neighborhood. Not, and these are the old cluster, of course, and this is the only the open star clusters, and they are detected in a very small region of the solar neighborhood, not very far off. So we can study the galactic structure using this star cluster, but only in the solar neighborhood. We will have in future, we may have the star cluster in distant regions, but so far our sample is very small. So the cluster younger than about 20 million year age, they remain in the parent star, and afterwards they start drifting from the spiral arms and fill the inter arms region. The deficiency of old cluster we have seen, and if you see the number, the total 91 old cluster we have found, and there were just 6. This is up to 1.8 kpc, and just 6 old cluster were found within 500 parsec region from the sun. So this is very small number of old clusters. So it is huge question why so few old clusters are found in the solar neighborhood, and it is believed that the clusters are distracted over time, and the less massive clusters are distracted relatively easier or in small time than the rich cluster or massive clusters. So we have found a typical number that up to the 4000 solar mass, so distraction time is the 700 million year, and if star cluster are massive enough, even more than 4000 solar mass, it will remain even a bit longer, and if it is less massive, it will distract even earlier. So this is the number we have got in the solar neighborhood. So it means our old cluster, which are beyond 700 million year old, if they are not massive enough, they will not live up to beyond 700 million years. And most of the, it means most of the clusters are less massive than the 4000 solar mass, and they do not survive beyond this age, and that's why we don't see many old clusters in the solar neighborhood. And the main reason for the destruction of the cluster in the immediate solar neighborhood, stellar evolution, and then of course in tidal stripping, they keep on losing the cluster members, and then spiral arm shocks, we have that kind of triggering events, and which again loses the cluster members, and then encounter with the molecular cloud also will stick the cluster with from their star. So in this way, slowly the cluster will disappear. It will completely fragmented. If you see the distribution of the cluster and the jet distribution of the cluster with the log age, you see the most of the young cluster are very close to the galactic plane, and with the age they keep on moving out the galactic disk. So open cluster are more confined close to galactic plane in the direction of, and the black one is the black dots are towards the galactic center, the cluster towards the galactic center, and the red one are towards the anti-center direction. So if you see the picture clearly, that you will find the more close to the galactic plane z equal to 0, and the red one are more scattered. So it clearly tells that the clusters close to GP galactic plane in the direction of galactic center, but they are scattered and tend to leave the galactic plane in the anti-center direction, which are the red one. And young cluster of age less than about 20 million year remain embedded within the molecular cloud. So the black one. So if you see the black dots in the young age regime, you will see that they are more confined to galactic plane. So these are the cluster towards the galactic center. So these 20 billion year remain in the galactic disk, and after that they start drifting away from the disk and scatter. So if you just the same picture, if you see here, we have average out the mean, we have determined the mean Z of those star cluster, and we have plotted the same diagram in the mean Z form. You can see that up to the 3 million years, the clusters are within the plane, and then they suddenly start drifting, and beyond this 300 million years, most of the cluster are quite far off from the galactic disk, and the line is 60 parsecs, so almost all the young cluster lie close to GP, and their distribution has a constant width of 60 parsec in vertical direction. So 60 parsec is the mean Z value for these star cluster, and thickness of the galactic disk, because this is up to 300 million years, and after that it is changing significantly, so we can conclude that the thickness of the galactic disk has not been changed for last 300 million years, and with time cluster move further away from the galactic disk due to factors such as tidal interaction with galactic disk and bulge, as well as mass loss due to stellar evolution. One other thing we have studied for the ragging in the star clusters, and as you see, this is the standard color diagram, and if you put this color diagram in any observed color diagram of star cluster, you can determine the extinction using this one, this is the value, and even you can determine the differential extinction, which is more prominent in the young star formation, young star forming regions and young star clusters, and in this way you can determine the extinction also. When I have plotted, I have drawn these star cluster in a XY diagram, their distribution, and the points are normalized to the extinction value of the star cluster. So these kind of pictures where you see towards the galactic center, you see the big dots, and most of the cluster formation is happening in these regions, and you have a lot of dust in these regions. This is toward the galactic center, and in the anti-center direction we have less amount of dust. When I calculated this extinction information, which we have found in the open star cluster with the ERAS 100 micron extension map, I found that it is within 5 degree latitude. It is very close to the skeletal map, and the skeletal map is just overestimated by 4% value, but above the 5 degree it is overestimated by a factor of 12%. So there is significant difference between the cluster extinction and skeletal map. We have also calculated this, the variation of the normalized extension, which is basically the EB minus P divided by the distance of the cluster. So we have put all the cluster at the same distance, and when we drawn it with the longitude, we found that in some direction we have the lesser extension, in some direction we have the higher extension. So EB minus B is highest in L equal to 50 degree and lowest in L equal to 230 degree. So, and the mean extension is only 0.17 into per kiloparsec towards 162 300 degree latitude range. And when I check the the distribution of extension in the galactic plane, I found that from the galactic midplane, it changes in the similar fashion in both the direction of the galactic plane, and this change is 0.40 plus minus 0.04 roughly for both the directions, so it is almost similar. And the important thing is that the 90% of the reddening material we found lies between the almost 430 parsec of the galactic plane, while the 90% of the total star cluster lies within 120 parsec of the galactic plane. And then we calculate the galactic absorption by doing the same thing, multiply by this RB, and we divided these small segments of 60 degree each in longitude and determined the maximum absorption in that region, and we plotted this longitude versus maximum absorption. So for each 60 degree we plotted this absorption, and where we found the maximum absorption in that 60 degree, we took that value and then we plotted this maximum absorption of the longitude, and we saw a sinusoidal curve, and here again, and the maximum value of that absorption is found at this galactic plane. So we have determined both K0, which is maximum absorption, and this is the maximum absorption at the value of Z. This is the Z value. So if you see the these two diagrams simultaneously, you will find that in L equal to almost 54 degree, there is maximum absorption, as well as it is shifted towards the north of the galactic plane. And while at L equal to 234, this is the lowest absorption, and it is shifted to the southward plane. The important thing is that when we draw a sinusoidal curve, it is not around the zero, it is not around the galactic plane, but it is shifted by certain factor. So this is called solar offset, which is basically the galactic plane defined by the Radioastronomy material is displaced by this factor from the actual galactic plane. This is the value 22.8 parsec, which is called solar offset. And when we draw this solar offset from various distance scale, we found that there is like variation in the different value of solar offset. We found the varies from 13 to 21 parsec for different distance scale. So it means though people have reported 6 to object, but we found that it also depends on the which kind of samples you have taken. And then we have determined the scale height also, and found that there is a scale height of 64 plus minus 2 parsec for the distribution of the open cluster. And when you exclude the old star cluster, which are basically are outside in the disk, then the scale height is just 60 plus minus 2 BC. And the scale height for the distribution of Radioastronomy material, we found that it is 186 plus minus 25 parsec. So the scale height changes also with the log h, as well as the these are two for the towards the galactic center and anti-center direction. So one thing we can see that when we report the scale height, particular scale height, it is very important that which kind of data sample we have taken, because scale height vary with the age, scale height vary with the sample, whether it is taken towards the galactic center or opposite to the galactic center. So, and it gives a drastically different value. Even here in this case, it increased by a factor of 5. So it means when we give the scale height, it is very important that we take full sample, otherwise bias sample will give you a complete different value of scale height. And we try to trace the spiral arm using the young star cluster, but it is not as good as Dambis has shown from the secret data in his last year paper 2015, and the spiral arms are quite visible, but using the star cluster is not as good as secrets, so we need a better sample or even larger sample for this, or maybe even the radio absorption of these regions give a better indication of spiral pattern. And well, I have also drawn the metallistic distribution of these star cluster to understand the chemical property. And what I found very interesting that this is the young, this is the intuited, this is old cluster, and in young cluster we found very poor metallicity also. In some cases it is indicated, while old cluster it is the some cluster where we have to found the high metallicity. So these two are unexpected, and we believe that this some enriching phenomena in the galactic disk is happening. So the material is coming in the galactic disk, while some of the cluster outside the galactic disk in the old age are maybe the interaction of other galaxy to our galaxy. So some of the cluster are from the different galaxy, which may show you the high metallicity even in old age cluster. So this is the metallicity diagram really with the galactocentric distance. So there is not a large sample. Normally the Lepin has found it two slope structure for the metallicity, but in our data we have not found any such kind of. But after we did this work, I mean, more elaborate catalog of metallicity and information is available. Hopefully in future, this work is for future, and we may have better picture of the real metallicity diagram. And the summary of the work is the cluster are key to understand the galaxy, but it requires precise cluster parameters. And MWSC survey is the one of the such project complete up to 1.8 kiloparsec. But we need many more survey and complete up to even larger distance. And 90% of the cluster lie within 120 parsec of the Radnick plane, and 90% of the Radnick matter lies within 430 parsec from the Radnick plane. It means that even cluster drifted from the galactic plane, they still contain a huge amount of dust and gas. And this is the minimum and measure, so like this 50 degree to 30 degree. The scale height of cluster will determine this. And now we have the Gaia data, and hopefully a better understanding of galaxy will be available from this. And thank you very much. These are the couple of telescopes which we have in our institute, observatory, and one you can see from the pictures. Thank you.
You clearly demonstrated that the population of open clusters as objects is heated with time. The dispersion increases. Yeah. What the main reason for heating is the interaction with giant molecular clouds?
Of course, tidal interaction with the giant molecular cloud is the main reason, and then spiral arm shocks are, so there's suppose some supernova event is happening in some spiral arms, because they are massive stars and within few million years, and they may last, and that will affect the other star cluster, because then the member of those star cluster will drift away. So because the shocks will dissipate those stars, will move those stars which are tidally interacted with this cluster, they will throw it out. So these kind of interaction happens in the
this mechanism is efficient for 3 rotation of galaxy. It is a lifetime of the cluster.
Yeah.
It is the population is heated.
Yeah.
Very efficient.
And within the lifetime of cluster, and they keep on changing their position. And with the time, they do not stay in their position. The spiral arms, they drift from the inter arms, and at the same time they lose the stars also.
Yes.
So with the time, they may completely evaporate also. So you may not find some old cluster, but only those clusters which are really massive one, they will stay in the outer part of the disk. So it means those clusters which were less massive, they could not reach to the outer part of the disk.
Also, it's very interesting that what you stated, that the metallicity of young open clusters differs drastically, and at the same time, in the same moment, we have the open clusters with very different metallicity, and the clusters are formed in disk, not in other galaxy, in our galaxy.
Yes.
And what is what is the interval of metallicities for the cluster? -1.
If you see
+1, I missed this.
Okay, this is the picture. So if you see
From
this
-1
is
to
-1 to +0.5. This is the center.
Really huge.
So this is the young cluster. These are the cluster with the less than 20 million year of ages. So we expect in the young cluster we expect higher metallicity. But here we see the lower metallicity also in these star cluster.
This is very interesting result.
Yeah.
That's from the point of view of theorists, I know that the mixing
yes.
of metals is very hard problem to mix even in our galaxy.
Yeah.
So it is just evidence of this.
Yeah. It clearly tells that this, because this significant peak.
Yeah.
And
very
this,
good.
yeah. And
So
this is also interesting that if
you can discuss then because
sure.
it's quite the
yeah. This work we have not finished. We are still working because we are expecting some more data on the star cluster for which we have the metallicity information. Right now, if you see we have just 10% of the cluster having the metallicity information. So if we can get more data on the metallicity, cluster metallicity, then we can enrich our samples and see whether this trend is still there or not, because this is the important thing, that you have the less metallicity open star cluster and high metallicity old cluster.
I have one question. So what is the typical age of the cluster with -1 metallicity?
See that I have not checked because the age part is not there. So but that I can tell you.
It's not that these are belonging to the thick disk population of the.
See, this is 20 million years. So less than 20 million. That is sure. This is less than 20 million, and this is more than 700 million years. So old I have categorized that more than 700.
Because it may be possible that they are belonging to tail of the thick disk population.
That I will have to check, because just I have taken the sample less than 20 million year and I have plotted it. So this is the work which I have not published as yet, but this is the thing which I have seen, and I thought that it is important to show it to the all audience.
Okay, so thanks again to this. Let's move to the last part of this session on Andre Davis on investigation of open cluster based on IPS survey data.
Well, the subject of my talk is investigation of open clusters using IPS survey data. Well, what is the problem that we face? We have several very extensive catalogs of open clusters. For example, the catalog by TIAS, already mentioned by the previous speaker, and another catalog by Karchenko Italia, which contains almost 4,000 open star clusters and with most of the important parameters determined for them. However, we so far lack a homogeneous and precise list of open star cluster parameters such as extinction, distance, and age. The problem with TIAS catalog is that it is compiled catalog, which draws from many sources and cannot be homogeneous. The catalog of Karchenko Italia is based on 2-mass photometry, which is not very well suited for estimating parameters of young open clusters. Netopil with authors compared several catalogs based on 2-mass data and found big inconsistencies among the results. For example, distances differ by more than 1 kiloparsec, ages by more than 0.5 dex, and reddening by almost 0.3 dex from those inferred by Karchenko Italia. Here, well, just I mentioned several automatic methods of cluster parameter determination, and I will just point out the first method mentioned here, Naylor and Jeffries, which I use in my work. Well, so far the best technique for estimating parameters of young open clusters is that based on UBV photometry. The idea is to estimate extinction from U minus B, B minus V diagram, and determine distance and age by hitting the appropriate isochrone for the cluster magnitude diagram. Just a few examples. M25 cluster. Here is how reddening is estimated, simply by shifting the color diagram to its theoretical place and determining the reddening amount. Once we have dereddened the cluster photometry, we can fit appropriate isochrome to it. Here, just another example, NGC 663, a more populated cluster, well-defined isochrones. And here, well, NGC 457, and another Berkeley 38. Well, however, many young open clusters are known to have non-uniform extinction, and reddening has to be taken into account somehow. The idea is to use the so-called Q method of Johnson and Morgan. The Q index is an index constructed based on color indices that cancels out the effect of reddening. Then once we have determined this index, we can estimate the intrinsic color and compute the corresponding reddening. The problem is that this method works well for UV photometry, unfortunately not for most of the photometric band combinations. The problem is that the reddening line in most of the cases is almost parallel to the line of intrinsic colors, and hence the two colors give you no information about reddening at all, because stars just move along the intrinsic color line. Sorry. Well, so now we come to the source of data that we choose to use. It is IFOS survey, which is covers North Galactic Plane, plus minus 5 degrees from galactic equator. Here are the main technical data. What I want to point out that we have 3 bands, 2 broad bands R and I. These are more or less SDSS bands, and a narrow band H alpha filter. The catalog contains about almost 220 million stars. Here is footprint. Okay. Here are just the filter transmission curves. We see this is R band curve, I band curve, and here is the H alpha band curve. Here is just the footprint of the survey as shown in the sky coordinates. This survey was already used to estimate extinction in different places of the galaxy. In particular, Sally et al. Constructed a 3-dimensional extinction map in the vicinity of the North Galactic Equator based on almost 40 million stars with the best quality photometry. The map has an angular resolution of 10 arc-minutes and distance sampling of 100 parsecs. And they estimated the principal parameters of each star. However, they point out that the data are only as a resource for target selection, for spectroscopy programs, or to gain insight into the origin of features in the extinction map. Just an example of the extinction map in a certain direction. We see extinction as a function of distance from the sun. However, as the authors point out, the calculation of all these parameters are subjected to a set of priors as well as on a survey selection function. They should be used with much caution and only as approximate estimates of the real parameters. Furthermore, the analysis assumes that space distribution is a relatively smooth function, and they map extinction at an angular resolution I mentioned already, and ignore the existence of open star clusters as spatially compact groups of stars with small scatter of ages. Well, we now proceed with adapting the Q method to our case. We have 3 photometric bands, hence two independent color indices, and hence only one possible Q index up to an arbitrary factor. Here we compute this for the case of standard Radioastronomy law, and here how does it look like? Sorry. What is the physical meaning of this index, however? We can write it in this way. So we have one pseudo magnitude and another actual magnitude and subtraction. This is sort of interpolation between R and I band magnitudes. We interpolate broadband magnitudes to the wavelength of H alpha. So we have a simulated broadband H alpha magnitude, and we subtract from it narrowband H alpha magnitude. So we have an analog of the famous Sternberg beta index with a reversed sign, which measures the strength of H alpha line. And now it becomes very simple, because hydrogen line strengths are known to be the highest in stars of spectral type A2, and hence H alpha index has a minimum at the corresponding color index. And this fact serves as a diagnostic tool for estimating the color excess. Here we show the theoretical isochrones of our H alpha index as a function of R minus I color for different ages from 6.0 to 8.5. What we see is that in this portion of the diagram, they all have minimum at the same color index, whatever the age, in very wide interval. Although the youngest isochrones are just slightly shifted in the vertical direction. Another interesting feature is that this portion of this color diagram is identical for all isochrones. We will use this fact later. This is just a zoomed in figure to show it in a better scale. Moreover, we find that this minimum is independent not only of age but also of metallicity. We computed it for isochrones of 3 metallicities, minus 0.5, 0 and plus 0.5, and found the position of the minimum be practically the same up to about 4 thousandths of a magnitude. Hence, we can use this tool to estimate the color index. Here is just the color excess. Here is an example of the cluster NGC 884. We plot the observed H alpha index against observed R minus I color. We see a very clear minimum, and we can fit an isochrone to it. The only problem is that should be taken into account that the actual distribution of data points is higher than the isochrone, and we find this to be a common feature, this vertical offset. But on the whole, it follows it very well, and we can determine the extinction value very accurately. Once we have determined extinction, we can use whatever color magnitude diagram consisted of magnitudes in 2 filters to estimate age and distance. For example, R minus I R. We simply dereton it and fit an isochrone. However, we have a problem with this particular survey because it's a very deep survey. It becomes saturated at about 13th magnitude, and therefore bright stars, the data for bright stars are not very reliable and usable, and this prevents accurate age determination for clusters based on this survey, but does not prevent the distance determination. We can partially mitigate this problem by using APAS survey photometry, which saturates at so the theoretical colors are okay, but they have to be slightly modified. And what to do if extinction is highly non-uniform, as is the case in many open clusters? Well, the idea is to use extinction-independent quantities. One is H-alpha index, and another is the famous Wesenheit function. It is magnitude plus a color term to cancel out the extinction contribution. So here again we have three younger isochrons, theoretical, this plane, and here older ones. And again we see that the oldest isochrons become indistinguishable in the faint part of the diagram. In this case, we have to try to determine age because we have no other information. Here just the example of two clusters which are known to be to have variable extinction. One is NGC 663. Note again this horizontal offset. H-alpha index should be the observed H-alpha index is greater than predicted by theory, as always. This is just a common feature. And here H4. Again, we see this horizontal offset and a very good fit to the isochron that allows us to determine age and distance. And what if we want to estimate individual color excesses of some stars? In the case of UBV photometry, we can do this for B-type stars, for the earliest type star. In this case, we can do this for H-type stars in this part of the diagram. You see, the isochrons are practically indistinguishable. Hence, if we know H-alpha index, we can determine R minus I. With the only condition that we should apply an offset to the H-alpha index. Here is just the domain of the diagram Wesenheit function again as a function of H-alpha index, and here the part of the diagram where we can determine individual color excesses. Sorry. Here just the same part on the actual diagram shown. And here our calibration. We computed calibration for the oldest isochrons, and here we show how the two youngest isochrons deviate from it. All other isochrons starting from 7.0 to 8.5 follow the overall line very accurately. Provided that again that we subtract the offset from the observed H-alpha index. Here is the distribution of color excesses in the cluster NGC 663 computed using this calibration, which is known to have variable extinction, and we see how how broad the distribution of color excesses is in this. Here just 884, the same point. We used this technique to determine the parameters of 18 standard clusters studied by many authors with using UBV photometry and with well-determined parameters, just to see how accurately our method reproduces the previous results statistically. Here we will plot our extinction values against published data. We see that they follow it very accurately. Identity line goes through our distribution, and well, no significant offset, and well, more or less acceptable standard deviation, given that many clusters have variable extinction. However, our extinction values are differ significantly from those implied by the 3D extinction map of Selli et al. Actually, our extinction values are by 0.08 magnitude greater than those implied by the 3D extinction map. Here is the identity relation, here is just the actual relation. Our distance estimates are about a factor of 1.8 shorter than published values, but this is mostly due to the use of different isochrones, etc. Overall, the agreement is rather good. The scatter of relative distances is about 0.1 or 0.12, depending on the diagram used. Here we show just how our distances compare to those published by previous authors. Only one cluster has discrepant distance. All other follow the line quite faithfully. The agreement of age estimates as expected is not so good. Well, we see that age scatter is very big, although the overall relation can be seen more or less okay. Well, finally, I point out that different isochrone fits yield consistent H-alpha index offsets, which differ by negligible amounts, several thousands, and with a very small scatter. And moreover, the scatter of these H-alpha index offsets among different clusters is also very small, about 0.014. So this can be interpreted as some general 0-point offset. Perhaps there is a mismatch between the actual photometric 0 points and those used for theoretical isochrones. It remains to be understood where the problem lies, either with the actual calibration of the survey or with some problems in theoretical computations. Well, at least one thing is clear, that these offsets have nothing to do with errors in the extinction law, because if they were due to wrong extinction law, they would be zero for zero extinction and increase linearly, but we see no trend with extinction over a very wide range. So here are just the results for 18 clusters. Yeah, just for some of the let's skip it. Not end. Well, the conclusion that we adapted the classical Q method of Johnson and Morgan to IFRS survey photometry to efficiently estimate the main cluster parameters and find the results to be very good, except for distances, except for ages whose poor quality is due to the saturation of the IFRS survey. The method is robust against age and metallicity differences in a very broad interval. We find a systematic difference between observed and theoretical extinction-free indices and derive a calibration for intrinsic color in terms of H-alpha index. Moreover, I want to point out that perhaps the systematic difference between our extinction values and those of the three-dimensional map may be due to this very offset of H-alpha line index, because Selle et al. Use it at face value and they do not correct it for this offset. And if we apply this offset and assume that most of the contribution for the extinction map comes from fainter stars, from A-type stars and not OB-type stars, which are less numerous, and use our calibration, then we find practically the same difference in extinction, about 0.04. So perhaps if they correct their data for this offset, the map can be okay. Well, thank you.
One question for curiosity. In the middle of your talk, you have demonstrated a view graph with dependence of mean extinction on the distance from Sun.
Yes, it was
Could you repeat this?
Oh, yes, this is from the map. It is sorry, it is near the beginning of the talk. It is just some arbitrary direction. I used it for illustration.
Exactly, this one. Is it arbitrary direction or it is average?
No, it's some direction. They published their map with a resolution of 10 by 10 arc minutes. So it's a window of 10 by 10 arc minutes.
I see. I see. That it could happen that some cloud or maybe
yes
appeared at the 3 kiloparsec and then you have this jump.
Yeah, this map is very, very detailed. It has a distance sampling of 100 parsecs and angular resolution of 10 arc minutes. So it is very usable for many cases. Unfortunately, it has to be corrected. And this correction might depend on distance, because it depends on the relative numbers of bright and faint stars, and the errors might differ for them.
But also there is some object. And
yes, here, and this can be found in many directions. You can use the SIMBA database Vizier, come to the catalog and print out, put in the coordinates and get such a view graph for any direction you want. It's very convenient.
So, what is the chance of contamination due to actual H-alpha emission from the disk of some of the stars in the cluster?
Sorry?
Is there a possibility of contamination of H-alpha magnitude for the continuum you are using for this color?
Oh, natural.
But actual gas in the disk of some of the stars actually.
Well, I ignore the possible contamination. The only, well, for the lack of time, I didn't go into details. The algorithm of Naylor and Jeffries takes into account binarity, the fraction of binary stars, the errors, etc. But it does not take into account gas emission. Might be. But actually, our extinction values on the whole, they agree with they do not differ on the average from those published. Unlike the extinction values from this map, they systematically differ.
So my impression, maybe I'm wrong, that your main outcome of this work, of this talk, is that IPASS at the moment is the most accurate, the best, how to say, the best model of the interstellar reasoning in all directions and so on. But I think that now you should to use the Gaia results, at least for the distances, the estimate of your
Unfortunately, not yet. Gaia results so far include coordinates, and parallaxes are given only for the Tycho II stars.
Yes.
So, and these sample a small region, and the parallaxes are not very accurate. They are more accurate than Hipparchus parallaxes, but they cannot compete with photometric parallaxes in most of the cases.
So it's not competing, with the photometric parallaxes.
No, I mean they cannot compete with them. The photometric parallaxes for stars with good photometric distances are better in relative terms than Gaia parallaxes. Gaia parallaxes for stars at about 2 kiloparsec distance, they have very big relative errors. So you cannot sample, you will not obtain such a good figure because you have huge error bars in distance terms. So we have to wait at least for 1 year. I don't know when good parallaxes appear.
So I will throw now the results, the press release of Gaia in my waste basket.
No, they are very good, but not yet for this purpose.
Yeah, sure.
Yes.
One question. So this theoretical isochrone that offset. So this theoretical isochrone which you have used from Sally et al. So have you tried other isochrones also, or do they exist for open clusters? You have used one set of isochrones, but what about different isochrones? They match with each other?
No, I use Padova, the most recent Padova isochrone as well, because it's rather it's the algorithm is rather time consuming because as most of the maximum likelihood algorithms that involve computing the distribution function by simulating hundreds of thousands of stars. But these are the most recent ones, just that appeared this year.
Okay, so let us thank all the speakers of this session. Before lunch break, we have an announcement.
So now we will have a lunch break, and after the lunch, we move to another room for Skype presentations. Yes? So it's more better equipped for this kind of conference.
You also deliver by Skype? You deliver the talk by Skype?
The next
Все, работает. Все это развалится, конечно, все равно прикольно. Это весело будет.
Говорит с РФСЛ.
Ай.
Все равно кажется, что это будет очень сильно фанить.
Да ничего не будет фанить.
Прям очень сильно.
Никит, скажи что-нибудь.
Что скажи, тут вторая камера не включена.
Нет, я
Дай, кстати, GoPro-шку. Не, ну она болтается все равно, конечно. Наушником твоим крым.
Скажи что-нибудь.
Ну, здрасте, до свидания.
Что-то не слышно.
How are you? Fine, thank you. Thank you.
Давай скажи еще что-нибудь.
Здорово, щеглы!
Что-то не слышно ничего. Порвешь слышно.
Может, ты плохо стараешься?
Нет, у меня есть как его, может быть просто отключен звук.
У тебя включен
Нет, у меня.
Всем привет. Второй день нашей конференции. Он оказался еще более сложнее, суровее. Да, Стань. Ну, в общем, короче, жопа, ребят, жопа, понимаете? Потому что вот я не знаю, как вот это будет работать, вот это вот RF-SLF. Даже не на изоленте, а на наушниках, короче. Вот пособие, как делать две камеры. Объясню, почему две камеры. Одна камера будет транслировать на YouTube, по второй камере наши скайп-докладчики. Да, у нас будут онлайн-докладчики, мы настолько крутые, что у нас будут онлайн-докладчики. И в скобочках нет. Вот, ну как это все делать, мы, конечно же, делаем в последний момент, придумываем. И получается вот так. И это реально трындец. Я не знаю, как это будет работать, особенно когда мы будем это поворачивать, когда будут вопросы
Инновация.
у зрителей.
Камеры скручены
Вот,
наушниками.
Всем очень нравится.
Так, Никита, кончай херней страдать, давай работай.
Херней страдать. Никита аут.
Скайпочки не настроила, уже
Да, там Игорь Иванович сказал, они не отвечают, те, кто докладывать будут.
какая разница, скайп нужно подготовить.
А мне можно фигней страдать?
Да.
Зачем
ты не сфоткал? Сука.
Урод это сделал.
Ой, мне кажется, он что-то там делает.
Так это стрим идет.
Да.
А что ты меня отключил-то?
А что его отключать?
Ну да, давай транслируй все, что я говорю, не говорю, стрим.
Чего? Понимаю, вешай. Так, слушай, мы с какого мы будем презентацию смотреть? С твоего, видимо, да?
Моего скайп, нет?
Скайп.
Или с ее скайп?
Так, я скайп зачем устанавливала? Объясните.
Да, тащи сюда свой скайп.
Тогда пускай настраивай ей. запись, там все дела, чтобы микрофон увидел от камеры. С моей презентацией.
Вы мне скажите, в ближайшие 1,5 часа я что буду делать?
То, что ты до этого ничего не понимаешь.
Презентация? Презентации-то нет теперь?
Нет.
Или есть? В смысле, а те, которые по скайпу?
По скайпу Никита должна быть.
У меня нет.
Презентация?
Как-то тебе на почту уже сыпались.
Чего мне на почту сыпали? Смотри.
Никита,
Куда его
тебе...
Алло.
Не связались? Взяли и смылись.
Так, ты поел, да? Ну что, я тебе это дело передаю, тут за что такое постоянно вылазит, просто не обращай на него внимания.
А что, там работает камера?
Камера работает, я проверял только что. Даже звук работает везде. Я даже звук настроил.
Я вообще не сомневался.
Да?
Да.
Зря.
Почему? Может быть, потому что ты не даешь. И ешь. Кошелек взял? Кошелек взял с собой? У нас 14:30, что ли? У нас 2 часа начинается. Ты правее сидишь.
Здесь? Почему здесь? Что я здесь делаю?
Здесь по кабине сидишь. Или ты здесь сидишь?
Господи, как бы неудобно, подвиньте немножко, не была.
Камеру, чтобы нормально видно было.
Она не нормальная? А как нормально? В смысле, чтобы...
Чтобы нормально видно. Желательно штатив. Понял тебя? Это что экран засвечивается, конечно. Скайп не видно будет вообще. Хотя ему не надо на свет, правильно? Себя точнее.
Может, кто-нибудь другой будет смотреть?
Ему не надо себя видеть. Правильно, ему не надо себя видеть.
Мне кажется, надо позвонить в колокольчик. Шуко, что ли?
Ох, ё.
Okay, so let's start next session, last session today. The first speaker is Zinchenko Igor, multi-frequency studies of high-mass star-forming regions.
Thank you. Okay, so I'm going to tell, as the weather mentioned yesterday, we have already rather long collaboration in this field. It was supported by several joint grants, as shown here, and as you can see, the topics of these grants are related to studies of the investigations of distribution of various gas components, ionized, neutral gas, molecular gas, and interaction between them. So in this talk I will present some results which are related to this collaboration. And here are the participants of this collaboration, and also some people who participate in these studies, not being involved in these grants. And as for objects which have been investigated in these projects, so they are listed here, main targets which were included in these studies. So it's several star-forming regions associated with H2 with zones of ionized hydrogen, like this. Most of them are rather well-known objects, and sufficient amount of data is available in the literature on these objects. And but I hope that we manage to get some interesting new results also, and I will try to describe briefly this. The observations have been performed at several facilities, which are shown here, and they cover the wavelength range from about 1 millimeter to about 1 meter at GMRT. It's 60 centimeters, like this, and 50 centimeters. And the angular resolution of these observations was from about 1 arc-minute to about 1/10 of arc-second. These are the latest observations which are now performed at ALMA of one of these objects. And the scientific goals of these studies are related to investigations of some problems which are connected to the description of the process of formation of high-mass stars. It is rather well known that when you try to describe this process of high-mass star formation, there are many theoretical challenges. And some basic questions maybe are listed here. So they include such questions as how to form sufficiently massive cores. Do they exist at all? Then how to avoid fragmentation of these massive cores, how this fragmentation process is going on. And then there are problems related to radiation pressure, which is imposed by this massive protostars at rather early stages of evolution. This radiation pressure can stop the spherical accretion. So some models are proposed how to overcome this difficulty, but all this requires observational tests, of course, and our work is mainly observational. So we try to observe these objects and to see what's happening there and how it is related to theoretical expectations. One of these objects, as I told, is this S76 region. So it is rather large H2 region, faint H2 region, and what you see here, it is the Spitzer 24 micron image, and the green contours show the free emission of ionized hydrogen. So this region of ionized hydrogen is surrounded by the dust envelope, which is seen in this mid-infrared emission. And there are two bright centers of star formation associated with strong infrared sources, which are marked here. This is better studied, this is less investigated. And this object was recently target for investigations of stellar content in this work, which is shown here. It is a publication of 2014, and it is a project which is devoted to investigations of massive star clusters in our galaxy. So this this picture is just jumped the previous. If you jump this picture by about 90 degrees, you will see something like this. So it is one region, another region, and so there are many young stars here, and they estimated the total mass of this stellar cluster at about this number, 2000 solar masses. And the age of this stellar cluster is estimated less than 5 million years. So, as I said, we studied this area in various continuum, in various molecular lines. So here you see the 8 micron continuum image, and also this radio continuum contours, which trace the ionized gas. And this insert shows in larger scale, this smaller scales, this area, and maybe here it is seen better. So these two sites of star formation, as I told, and so here you see that inside this large shell, rather extended shell, we see a smaller shell here, and the impression is that the expansion of this large shell triggered the process of star formation in this area, and here a new star is born, and it creates a new expanding shell here. So here we see this green contours, this GMRT data, which show again the ionized gas, and this yellow contours show the 1 millimeter dust continuum emission. So here we see all this. As I told in the beginning, we try to investigate the relations between ionized gas, neutral gas, and so on. So here we can see this, can compare distribution of these different components, and to see that they really interact here somehow, and so on. This is another side of this star formation, less investigated, as I told. But it is the same area at closer look. Again, we see here the ionized gas emission and this molecular emission. So the molecular emission is concentrated here. We don't see any molecular emission in this area. And so this, in general, this site looks like a good example of this sequential trigger star formation. And at still smaller scale, with interferometer, when we observe this area with interferometer, this small part, we see that it splits into several clumps, like is shown here. The masses of these clumps are several tens solar masses, and the evolution stage is apparently different. So, say this clump, the strong infrared sources observed, water masers, and so on. Here we see only, there is no infrared emission here, strong infrared emission here, but we see water masers, and here is nothing. So the impression is that the star formation propagates from here to in this direction. So it's more or less corresponds to the expansion of this H2 region. So again, it can be considered as an indication of this trigger star formation. And on large scales, we mapped the whole area in the CO lines and in the isotopes, CO isotopes. And so this is the map in the certain CO isotope. It traces well this dust shell. And in the main CO isotope, we also see such ring structure surrounding the ionized region. And if you look at the spectrum in 12 CO, in 13 CO, it looks like this. And first I want to mention the following. So the velocity which corresponds to this dense gas, it's about this 30 kilometers per second. Then there is this peak. It is not quite clear whether it is related to this expanding envelope or not, but the velocity of the ionized gas is about here. It's 23 kilometers per second. So it looks like perhaps we see two sides of this expanding envelope, but the expansion velocity in this case seems to be maybe too high. It's almost 10 kilometers per second, which for such large scale seems to be too large probably. But another moment which I wanted to tell about is that if you look at this picture, you see that in the center there is a minimum of the emission in the center. It means that the envelope is transparent in CO, yes? But if we compare the 12 CO and 13 CO, the ratio of intensities in these lines is this just much less than the isotopic ratio. And it indicates the high optical depth in 12 CO. So there is an indication from one point of view that the optical depth is low, from another, from comparison of these isotopes, it should be high. So, and these two things can be explained in assuming that the envelope is clumpy. And so these clumps have some filling factor, and they are optically thick. But since the filling factor is low, sufficiently low, we can see the effective optical depth can be also rather low. And we also observed this northern component, as I told, this one, and we see the enhanced molecular emission here, as shown here in H2, in 13 CO. I probably will skip this, it requires more analysis, these observations of this part. And another object which was investigated during this our joint project, it's this W40. It was made mainly by Lev Pirogov, who investigated this object, and looks interesting. One interesting thing is that we see here this fragmented envelope divided to many clumps, and the properties of this fragmentation, parameters of this fragmentation, they more or less correspond to theoretical expectations for expanding envelope around H2 region. And here we see also the signs of interaction between the ionized gas, which is traced by these red contours, and the dust emission, which is this gray image. It is dust emission. So apparently we can witness here the interaction between this expanding H2 area and surrounding dust envelope, which leads to density enhancement here and probably again to triggering star formation. Another object which we started to investigate recently with Dr. Manos Samal mainly, it is the so-called infrared dark cloud and filamentary infrared dark cloud. So it is not far from this S255 star forming region, and in the part of this star forming complex there is a rather long filament is observed several parsecs in length, and here you can see this again mid-infrared image. There are some mid-infrared sources here, and this is the map in CS, map of the CS emission, which shows this elongated structure tracing this filament, and it is split into several fragments. And the estimates show that again that masses of these fragments and the parameters more or less correspond to theoretical expectations. So the theory tells that these filaments, cylindrical filaments, they will be unstable if the linear mass, the mass per unit length, exceeds this critical value, and if to make the estimates of the observed masses of these objects and this critical mass, so it turns out that it should be unstable, and so what we see here, it corresponds to this picture of fragmentation of filaments into these smaller clumps. And here we see the radial velocity, the projected velocity along the line of sight, and this picture shows that we see here some movements along, just movements along these filaments, which can reflect this process of instability and fragmentation. And recently, just about a week ago, Peter performed additional observations of this object at the 30-meter Iran results soon, which can show better this process of fragmentation on this object and can help maybe to better understand what's happening there, including all these kinematics and other properties of this object. And it is another example of such filamentary structure, another infrared dark cloud, which we observed in the southern hemisphere. And here again we can see signs of such process of fragmentation. So here we see along this filament you can see almost at regular intervals, at equal intervals, these mid-infrared sources, young stars, which probably appeared due to this process of instability of this long structure. We observed this object also in continuum on various molecular lines. Here, this is continuum image, this is the image in the N2H plus line, and it shows this also molecular and dust clumps and estimated their parameters. And again, these estimates show that it more or less corresponds to what we can expect. So it agrees with the theoretical expectations for fragmentation of such long cylindrical structure. The object which we studied maybe in most details is this S255 area. So this rather well-known star-forming region, it is such dense, several dense condensations, which seems to be located between two large expanding H2 regions. So probably it is just a compressed layer between these expanding H2 regions, as Andrei has shown us in the morning, that these expanding regions can somehow interact, and between them you can get such dense layers which where the new stars can be born. So here we probably see something like this, and there are two main condensations here, and with single dish observations with single dish give masses about 300 solar masses for each of them, temperature, similar temperatures and so on. But when we look, this shows maps of this area in various molecular lines, and we see significant differences in various lines, which corresponds to so-called chemical differentiation. I will not tell much about this, but in continuum they look very similar, these two condensations. And we observed we observed both with interferometer, but this one may be in more details. And here you can see this this clump. It splits into again several cores, at least two main cores. There are some additional cores also here. This map is obtained with even better resolution. The resolution about 0.4 arc second, and this this core is the main center of activity in this area. It is rather dense, hot, and so on, and the estimates of the temperature show about 150 K, and So, and when we look at the kinematics of this object in various lines, it shows such clear rotation around about this axis. And this axis, it shows the direction of jet, which is observed here in infrared and so on. So there is a rather well-known jet here, which was observed earlier. And here, the scale you can see here. So the size here about 1000 AU. And if we look at the position velocity diagram for this core along this cut, so it looks like this. And the mass of the central object is estimated at 20 solar masses. It's from fit to the spectral energy to the CAD curve. It was made by Manash. And so it more or less corresponds to Kepler law, but the angular resolution is still insufficient. So the size, the beam is comparable to the size of this object. So recently we observed this area, started to observe this area with ALMA. This is shown, this spectrum shows the ALMA results with had sufficiently compact configuration, rather low configuration, and here the angular resolution is also about 0.5 arcsecond, and now we are expecting for much higher resolution data at about 0.1 arcsecond, which, as I thought, they have been made already, but the data not available yet. And you see that the spectrum is rather complicated. So the target, the main target was this line. It is this CS isotopic line, C34S. But there are also many other lines here, including methanol, some other things, and so on. And all these lines, the distribution of these species is apparently different. All of them show this rotation. Also, this, like this in CS, for example. So, and the temperature here is estimated from CH3CN at about 130 K. It was also estimated, the physical parameters were estimated by our colleagues, by Svetlana Sali and Andrei Sobolev, using their models for methanol emission, and so they estimated temperature and so on. And the interesting thing is that according to these estimates and also to this, the beam filling factor is very low. Here it is about 0.2, here it's about the same, also close to 0.2, and it means that the source is very inhomogeneous. So apparently it consists of several clumps which don't fill fully the beam. And it's rather interesting thing, and I'll tell a bit more about this later. Then we see a nice outflow originating at this object. Actually, when we observe this outflow with the SMA, with the interferometer, we obtained a rather strange picture, that it looks like this outflow originates somewhere here, not at this, where it should be. But when we observe the same with a single dish, we run with a 30-meter antenna, the picture is correct, I would say. So it is just some things related to interferometric observations, because interferometer lose information on diffuse emission and so on, so probably it's related to this. So we see this nice outflow. And we see also how this outflow interacts with the surrounding medium. In particular, this contour shows the N2H plus emission, and it's clearly seen that N2H plus is absent in the area of outflow. But it is not the case for CS, for example. The distribution of CS is not affected by the outflow. So it's chemical effect of the outflow. And the interesting thing is that we see here concerning the mechanism of this outflow. The position velocity diagram for the outflow is shown here. And there are several models which try to describe the origin of such kind of outflows. They are briefly shown here. I have no time to describe in detail. So there are so-called bow shock model, turbulent jet model, wide-angle wind, and some other variants. And in our case, the most appropriate model seems to be this model, so-called jet bow shock model, which describes best the structure and kinematics of the outflow. And we see here the signs of the two outflow events, of two ejection events. And actually, this second event is also traced in this on smaller scales in the emission of, this is a map of H2 plus emission, and also the ionized gas as observed with GMRT. So, and these black contours show the emission of the ionized ion, which require high temperature, high density, and so on. So they trace these shocks originating when the jet propagates, it creates these shocks, and we observe them here. So apparently we see here these shocks at small scales. And there are also molecular emission related to them. And recently also a paper was published, which it's still smaller scales, just here. Investigations with the VLBI technique observations, they show distribution and movements of the water masers in this area. And these observations show clearly next event of this ejection event, traced by water masers. So, third at least. So, and recently also was such interesting data have been published that about the methanol mother flare in this object, and also the infrared emission burst observed here. And all these events are apparently related, and they hint at the episodic events of accretion and ejections apparently in this object. And actually, as they say here, it's the first case of FU Orione type event in such type of objects, of high mass forming objects. So it looks very interesting, and it supports this idea of fragmented disk and these episodic events of accretion and ejections. And also some people are developing theoretical models of such disks around massive protostars, and they obtained also this picture of lumpy fragmented disks, structures which correspond well to this observed picture, hopefully. But we hope that the observations with high resolution can understand better what's happening here. Also, the northern part of this S255 area looks quite interesting, and Peter will tell more about this. And here you can see many contours and so on. I guess that he will explain what is shown here. We see here also dense core, outflow, and so on, and ionized gas and other things. Rather interesting area, but less investigated than the southern one. And finally, I show one slide about another object, S187, which we also started to investigate. Here you can see, this is again the 8 micron infrared image, and we observed this area in molecular lines. Its green contours is the N2H plus emission, and the yellow contours show the dust continuum emission at 1 millimeter. So we tried to observe that at GMRT in continuum, and also in the line of neutral hydrogen at 21 centimeter, and the line was, it seems that it was detected, and Nikita will tell some words about this. I will not tell more. So, and finally, some conclusions that I think it's important to emphasize that such multi-frequency observations are essential for understanding this high mass star formation, as we tried in the framework of these joint projects. And it seems that the formation of stars with masses at least up to 20 solar masses is more or less a scaled up version of Loma star formation. There are signs of Tigris star formation, and fragmentation is observed on various scales, from rather large scales to smaller scales which are observed, and it is apparently an important process. And we see also signs of episodic accretion and injections in this area. Thank you.
Some questions? Does anybody have some questions?
So you mentioned that some quantum structure in the disk based on methanol modeling. So is it possible to somehow to check this with dust calculation? Let's say calculating spectral energy distributions to support the idea that the disk should be quantum.
You mean from observations?
Yeah, from observation, from modeling.
Well, from observations or from modeling, because, well, from modeling, I guess that you can try to do this, to obtain this model for dust emission and so on. But from observations, well, we have data on several wavelengths, and it is unfortunately not too many. So no detailed spectrum for dust emission can be.
So 0.2, it's quite low, right?
Well, 1.2 millimeter we mainly have. There are also data at shorter wavelengths. For example, there's cube observations at 0.8 millimeters and so on. So at least 2 or 3 points can be taken, but it's probably not sufficient to compare with detailed models.
Any other questions?
No.
Okay. So this filling factor, it is actually not the filling the beam. It doesn't mean the clumpiness. What do you think? Is it really clumpiness, or it is just imperfect filling of the beam?
Well, of course it's just imperfect billing of the beam from observational point of view. Well, the other things are just not speculations, but it's already some such assumptions. Well, so from my point of view, the most natural assumption is of this clumpy structure.
So increase of angular resolution will solve this question.
I hope so.
Yeah. That's answer. Thank you very much once again. Next speaker is Lokesh Divangan.
Yes.
Yeah. Lokesh.
Yeah.
Do you hear us?
Но он нас не hear, лучше позвонить надо.
No, it's possible with YouTube, but we should have a call. I don't know. Skype is.
Там, да. Видимо, переключил тебе экран.
Да какая разница?
Вот Локиш мне что-то написал. Вот Локиш пишет, что я на онлайн on Skype.
Так они то же самое говорят.
Просто что-то скайп, не скайп.
Вообще ничего не
Скайп не скайпирует.
Так, Ольга, да? У тебя логин Ольга?
Нет.
Вы пока презентацию замените.
Никит.
Надежная. Он же оттуда не может? Нет, смотри.
Ну, классно. Почему он частично работает?
Нет.
Почему здесь мушку не вижу, а там вижу? А здесь
Потому
вижу,
что
а тут
она
там нет.
заразна.
Что за бред?
Кошмар какой. Тут у нас какие-то технические проблемы. We need 5 minutes to reboot the computer.
Может, вам больше времени надо, когда мы
Нет,
Ивана Евгеньевича
нет,
запустим?
нет, нам буквально минутку нужно перезагрузить компьютер. Почему-то он завис.
Нет, я говорю, может быть, вы пока решать будете эту проблему, а у нас Лев Евгеньевич, и тогда все настроится.
Потому что это разные
Так или не
мониторы.
так?
Нам нужно всего 2 минуты, насколько я понимаю.
Он попадет потом снова.
Что?
Потом блоки что попадет, потом
Вот видишь, почему я там открываю?
Нет, он как раз
Никита,
настроится.
презентацию открой.
Ну, слышишь, чисто технические проблемы, которые они могли бы сейчас решить, о которых сказали.
Так, офис, да, сейчас будет?
Вот в YouTube написано Нижний Новгород, спасение кота. Это не то? Не та ссылка.
А как логос переводится?
Нет.
Может, это так переводится?
Компьютер плохо. У тебя долго спускается?
А с ними связь есть?
Связь есть, да, мы предварительно, правда, не созванивались.
Ну, там можно ее включить.
Игорь Иванович, если у вас есть с ним связь, вы не могли бы набрать ему скайп, он бы у вас подсоединили к компьютеру через HDMI?
У меня нет.
Нету?
Вот нет, вот есть что-то. Сейчас попробуем.
Мы бы тогда и звук, и все остальное вывели через вон тот замечательный телевизор. Нет, слушай. Так, мы провалились.
Так у вас есть он там скажет?
Да вроде есть, да.
У меня тут что-то не дозвонилось.
Очень смешно, Никита. Очень смешно.
Я смотрю, всякие конференции наших работников. Европейцы изобрели прибор для анализа качества жидкости. Я читаю.
Тоже проанализировали.
У нас еще интернет отвалился.
Да, это...
вот он пишет.
Ну хорошо, мы сейчас можем ему позвонить.
Так, увидим.
Сейчас все увидим. Это первый раз, когда мы по скайпу. Hello? Did you hear us?
А звук-то есть?
С него есть. Did you hear us?
Скажи ему, пусть говорит.
Hello? Can you hear us?
Hello?
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 У тебя, может, там что-то не то с микрофоном?
Нет, вообще слышно, по-моему. Или нет?
Их там много.
Скажите что-нибудь вот прямо вот сюда, вот, пожалуйста.
Hi, Lokish. Do you hear us?
Может, тот микрофон?
Который?
Микрофон, в принципе, должен быть на ноутбуке, его ничего нет.
Да, все было нормально. Все, с вебкама забирает звук. От этого звук идет, созванивались.
Это вот у нас хороший был с вебкама.
Да. Вот. Все забирает.
Три раза было по скайпу.
Ты на весь экран извини.
Hello?
Hello?
Are you able to listen to me?
Yes.
Погромче.
Yes.
I can't hear you.
Hi Lokish, do you hear us?
No. We hear you.
Он свою презентацию видит с экрана?
Ну, как сложно.
So I'll start now. I'm unable to hear you, but I can present my talk. If you say yes, then please write me.
Type yes.
First slide, yes. Yeah, I can see the slide now. Press button below to start your video. Shall I do that? Okay. Okay, so now I'll start. Okay. So thank you very much for this opportunity. So in this presentation, I'm going to talk about the work which we have been doing related to star formation. So in this talk, I'm going to present results related to one of the star forming region that is known as S235. In this work, we have a collaboration with Professor Ojha and Professor Andhra from India. Then we have a collaboration from Mexico, Professor Maya and Professor Luna. So in this talk, next slide.
Next.
No, please go back. Please go back.
Okay.
Please go back one slide. Yes. Okay. So next one. Yes. So in this talk, I'm going to focus on the following points. I will in the first point I will actually present the brief of the presentation. Then I will talk about the objective of my work. Then the source selection and the discussion. Then some work approach, the results I will talk about, and finally I will summarize my results. Please next slide. Next slide. Okay. So in general, stars form and dust in molecular clouds. Please go back. Okay. I'm sorry for this disturbance, but now I am now continuing. So stars form out of gas and dust in our giant molecular clouds, and these stars are categorized in different masses. Like in general, we categorize low mass star and intermediate mass star. Mass less than 8. Stars having mass more than 8 solar mass, they are called massive stars. So in general, massive stars have a significant impact on the evolution of the galaxy and universe through their energetics. So they are the source of ultraviolet radiation. So in general, expanding astrophysics and powerful outflows, and also they explode as a supernova explosion. So they emit lots of energy to the surroundings. So through their energetics, they can actually interact the surroundings. So they can positively also they can interact, so they can generate new generation of star formation, and also they can interact negatively. It means they can disrupt the molecular clouds and halt the star formation if it is going on in that cloud. Please go next slide. Next slide, please. Yes. So yes. Okay. So as I mentioned, the massive stars has a positive impact and negative impact. So they can generate a new generation of star formation, and you can say they can build a formation. So, but the question is how they interact and what are the physical processes by which actually they interact and feedback to the surroundings. So that is still unknown. Please go. Next slide. Next one. Next one.
задержка или конечно?
Да, надо его просить отключить камеру, просто пускай он только говорит, потому что много интернета ест.
Next one.
Давай следующий.
Okay. So the massive star, yeah. So massive star can interact to the surrounding, and they can trigger the new generation of star formation. So the triggering process in general are explained by these three processes. One is known as collect and collapse. Another is known as the radiation driven implosion, cloud collision. So please go next slide. So in collect process, actually the massive stars, when they form and they expand in the surrounding environment, so this expanding actually accumulate the material, and with the time actually this accumulated material fragment into different condensation, and that condensation starts leading the formation of stars. So that is explained by this process. And please go to the next one. The second one is the radiation-driven implosion. It means you have already pre-existing material where this massive star explode and they expand. So the expanding region actually explode to the existing material and they trigger the star formation. So this is explained by this RTI. Please next one. And the third process is the cloud-cloud collision. So you have two molecular clouds, they actually approach together and they collide, and you can say interaction of the clouds, they trigger the new generation of star formation. So that is one of the process which is also explain the trigger star formation. Please go next slide. So based on this introduction, I am going to present the work which where we actually look for how the physical process governing the interaction and feedback effect of a massive star to its surrounding. So we want to study how the massive star actually triggered the new generation of star formation, whether it triggers or not. So that we would like to study. And another thing also we would like to search for this observational proof of trigger star formation by the massive star. So these are the objective. With this objective, we have selected next slide. So with this objective, we have selected a source, and to studying this physical process, we utilize the multi-wavelength data covering from the near infrared to the radio region. So this data will very useful to trace the molecular gas, ionized gas, dust, you can say warm dust, cold dust, and also shock emission regions, and also we trace the young embedded stellar population in a given star forming regions. So please next slide. Okay, so for us, as I mentioned that I am going to focus on one star forming regions. So why I have selected this region? This you can see this big molecular cloud is known as G174 plus 2.5 is actually located on the Perseus arm and is very extended star forming regions, is very star forming regions, and is actually relatively nearby star forming regions. Distance actually people have measured 1.82 kiloparsec for these regions. Please go to the next slide. Next. So these extended star forming regions contains two sub-star forming complexes. One is known as S235 complex. You can see the highlighted box in the figure, and also there is another star forming region is known as the same complex. But if you estimate their velocity, so this S235 AB region is traced in a velocity range from -17 to -15 km per second, and whereas the S235 complex actually traced in velocity range -23 km to -18 km per second. So you can say that this S235 AB region is the red shifted compared to the S235 place. Please next slide. So now I will present the morphology and using the different wavelength images of this S235 region. So you are actually able to, you are looking at the optical image of the region S235 star forming complex. The box which I highlighted in that, so that region is zoomed here. You can see this optical image and you are able to see only the nebulosity. Now go to the next slide, please. So now this is a combined optical plus infrared. So when you combine the optical with infrared, actually you penetrate more, because when you go towards the longer wavelength, you actually penetrate inside the gas and dust. So you are able to see more and more embedded sources and nebulosity. So you can compare with optical. Now you are able to see more embedded sources as well as nebulosity. So if you look at this morphology, it looks like a sphere-like morphology. Please go to the next slide now. So now this is a infrared plus radio. In infrared, you have actually traced the spiral-like geometry. Now we have presented the radio emission. So this is the GMRT 610 megahertz radio continuum map, which is overlaid on this infrared images. So it nicely located within the sphere-like geometry. So the ionized gas, or you can say this radio continuum emission, actually traces the ionized H2 region. So that is well located within the sphere-like geometry, and also you are able to see the different components we have labeled here: eastward, east to north, northwest, southwest, and other sub-regions. Please go to the next slide. Okay, and also if you see the image, the massive star, which was already known earlier, was actually located at the center of this sphere-like morphology. So if you look at the morphology, it is very promising, because the massive star is almost located at the center of the sphere-like geometry, and an H2 region is located within that. And you are also able to see the embedded sources along that sphere geometry. Now, using this GMRT or radio continuum emission, one can measure the Lyman continuum photons, which will allow you to know the spectral class of the source. So we have utilized this radio continuum data, and actually we measured these Lyman continuum photons, and we obtained an exciting source of this region is 09.5, which is actually also earlier known. So it's actually confirmation that our data also confirm the region is excited by this radio spectral type 09.5 source. Massive stars. Please go to the next slide. So we have seen, so far we have seen the optical and infrared images of the same region. Now we actually am presenting the dust continuum map of this star forming complex. So it is very important to note that this earlier whatever map was published in this region, where we have not seen all the condensation along this sphere like the morphology. Here I have highlighted one circle, big circle. Actually that traces, or you can say depict the sphere-like morphology here. If you look at carefully this dust continuum map, which traces the dense region, you find condensation almost along this cell-like sphere-like morphology. So we have labeled here all this condensation in this map. Please go to the next slide. So now we wanted to see also the condensation using the extinction map. So we have utilized the available Euclid's GDP galactic plane survey near infrared data for this region. So we have utilized, and actually we made a near infrared extinction map, and we found this extinction map was measured using the color axis of the two bands, near infrared bands. So this resultant map actually shows several condensation, and I have marked a circle here which actually traces this sphere geometry, and you can see the condensation, where the condensation are located here. So if you look at this carefully, you will find that actually the condensation are almost regularly spaced distributed along this sail-like structure. And there is another reason, east one is little away from the sphere-like geometry. And also if you look at the southwest and the south region, they are little away from the main spherical-like geometry. So if you also I have marked the position of the massive star, you can nicely see the position of massive star is almost located at the center of the sail. Please go to the next slide. So as I mentioned that we have utilized this Euclid's GPS data and utilized the color axis equation to estimate the extinction, and so we have observed HK axis from our observed data, and also we have measured the intrinsic from nearby control field, so that gives you color action and converted into the extinction using the extinction law. Yeah, please go to the next slide. So for this extinction map was actually created by the mean value of 40 nearest neighbors stars. Please, next slide. So as I mentioned, this molecular cloud is associated with this S235 complex is a trace in the velocity range of -23 to -18. So we have integrated that, and you can see the integrated map here. So this all the condensation which I marked in the sub regions which are highlighted on the other images, you are able to see here the south, north, east 1, east 2. So these regions are also placed in the molecular cloud, as we have seen in dust continuum, as we have seen in the extinction map. Please go to the next slide. So now we want to explore the signature of a star formation. So for that, here you are able to see the ratio map made using the RF first two bands. So RF 4.5 micron is actually divided by 3.6 micron image is a ratio map. So here, when you look at the bright region, it means the 4.5 micron is dominated. It means the 3.6 micron is dominated. And in general, this 3.6 micron contains a 3.3 pH line. And also this 4.5 micron band contains very two important lines. One is 4.05 is the Beckett, and another is 4.69 is the H2 line. So this 4.5, if you in the ratio map, if you look at the bright region, so it means Beckett alpha and H2 could be dominated. And in 3.6 micron, if it is a dark, because it is in a denominator, so dark region faces the pH excited region. So the bond three of the scale is nicely traced in this black region. So basically, one can think about the pH emission. So what this map traces is basically we know the ionized emission is actually located inside this sphere-like space. It means we are actually able to see the photo dissipation region here. Please go to the next slide. So this is the continuum subtracted H2. This is the molecular hydrogen map. This is the continuum subtracted map. So here also you are able to see the same sphere-like geometry here, and also at the edges you are able to see the outflows. So here I have collected three. I have actually marked the 3 boxes here. You can see 3 boxes. That has been zoomed in the next slide. But here you can see there is an outflow activity on the edges of on this cell-like morphology. Please go to the next slide. So in general, this molecular hydrogen is actually excited by a fluorescent or shock. So shock emission always explained by the outflow activity. So here, as I mentioned, there are 3 boxes was zoomed here. 3 is to 1 is 2 and northwest another bottom image. So here left side is actually H2 and the middle one is Spitzer band, and the right one is actually 24 micron each. So here in left side you are able to see the outflow activity, but the driving force one can trace in the last 24 micron image. So driving force is also traced in this map. So there are actually very young and embedded sources are present at the edges of the region. So please go to the next slide. So this image itself traces by the presence of young stellar sources, which actually they excite these outflows. So in general, observationally, when we say wires embedded sources, we always talk about the young stellar sources, which we always assume, okay, you have a star and around that you have a disk and envelope. So when the star emits light, so always we trace the color axis using the infrared bands. So that indirectly allow us to trace the embedded population using this color axis. So here one theoretical cartoon is presented. They are actually classify different evolutionary stages of star forming sources. So youngest one known class 0, which has an envelope, then class 2, class 1, class 2 sources subsequently. So envelope mass actually is fed up and disk emerges with as they evolve, and also when it goes to the main sequence, it disrupts the disk. And the embedded sources, as I said, it has an envelope and the disk, so it emits. If you look at the spectral spectral energy distribution, it peaks in the longer wavelength. So you need a longer wavelength to trace these embedded sources. Yeah, please go to the next slide. So here we have utilized the near infrared and mid infrared color diagram, color magnet diagram to trace the sources which having the color axis. So using this different color and color diagram schemes, actually we have identified the young stellar sources, and then we have actually studied their spatial distribution on the images. So please go to the next slide. So here this is an extinction map where we have overlaid all the identified, or you can say color axis sources on the map, and also we have studied the surface, the clustering of the sources using the method is called surface density map. So we have utilized this map, and actually we are able to see the clustering of sources in this image. So you can see the most of the sources are mostly distributed on this the sub-region which I highlighted earlier along the edges of the sphere-like morphology, as well as there is a significant sources but without clustering also seen in the north and other regions where the condensation are seen here. So one can say that is very nice special correlation between the forming young stellar sources, clustering of sources with the dust or embedded clumps. So there is an ongoing activity on the edges of this sphere-like morphology. Is almost, as I mentioned, the condensation are almost distributed like regularly in space manner. So this star formation activity is also associated with those condensation. Please go to the next slide. So this, as I mentioned, this the clustering of the sources is actually generated using the special use the nearest neighbor method. So we have utilized this standard statistical approach to identify to study the clustering of sources. So we have selected we generated the nearest neighbor, and then we computed the surface density map. Yeah, please go to the next slide of all our identified sources. So far we have seen, okay, so far we have seen the star formation signature, morphology of the complex. Now we'll see, okay, there is S2 region. So does the S2 region expand or not? So for tracing this expanding S2 region, we have utilized the molecular line data to study the expansion of S2 region. So this is an integrated map. You can see the S2 region and the location of the massive star is almost the center. Now here this is a position diagram of the region. Please go to the next slide. So here I am presenting position velocity diagram using the 12CO and 13CO. The left side is actually 12CO and right side is 13CO. So the top one is RA and yeah, I think it's RA. Yes. So top left side, that is x-axis is your velocity and y-axis is your alpha. And similarly in the right side also, but using 13CO. Similarly in the bottom map is a declination, and y-axis is a declination, and x-axis is a velocity. So in a declination and velocity map, is actually alpha is integrated within a velocity range. So you are able to see, and this map actually shows a semi ring-like structure in the PV analysis. You can see carefully. There is a ring-like or C-like structure. Oh, I am talking about overall seen in the PV diagram using this both molecular lines. So using this morphology, we compare this with the theoretically predicted signatures for the expanding cell. So please go to the next slide. So you have able to see the semi ring like structure. So this, and also along with this overall structure, we have a sub regions where the velocity gradients are seen. That could be outflow activities. Please go to the next slide. So what does this semi-ring or C-like structure represent in the PV analysis? So for that, actually I will visit one paper is called RC et al. They studied such observed structure in Perseus molecular cloud, and they said that such structures are actually represent the expanding bubbles in a turbulent medium. So this is the expanding cell. Now, if you consider the morphology, you have a massive star or S2 region located within that cell. So it means this S2 region and this expanding cell is actually related. So one can say this expanding S2 region is associated with this region. Please go to the next slide. So as I mentioned, this considering the velocity structure and the amazing O9 prime star, the C-like structure in this complex can be explained by the expanding S2 region. So now we have seen there is expanding S2 region. Please go to the next slide. So now I'll revisit this map. We have seen the several condensation along the sphere-like morphology here, and if you look at this, apart from this east one region and south region, almost other sub-regions are almost located on the sphere-like geometry. So based on this study, and also we have actually estimated the dynamical of the S2 region, that is 1 million here, and in general, we know the Youngster sources, their ranges like 0.5 to 3 million here, 1 to 3 million, depending on their sub-classification. So there is a possibility of biggest of in the region. But if you consider the east one and south and southwest region, they are actually away from the sphere-like geometry. So if you just consider now east one region, in general, there was a study by Kirsanov et al. In 2008. So this east one region is actually youngest sub-region among the other star forming regions. So this east one could be pre-existing. So that region that was actually triggered expanding S2 region. So there is a possibility of collapse and collapse as well as RDI process in the complex as I explained this process, physical process in introduction. Please go to the next one. Please go to the next one. So, except east 1, northwest, southwest, and south region, the sub-region can be explained by the collect and protest scenario. But the eastward region could be as an RDI, so you can go to the next one. Yes. So if you look at this integrated map molecular emission of the whole entire cloud, S235 as well as S235 AB region. As I mentioned, AB region is placed in the velocity range of -17 to -15 kilometers, and this S235 region is covered in -23 to -18. So now just look at the right side, there is a PV diagram. So in the PV diagram, you are actually able to see two intensities, peak of the intensity is connected by the intermediate velocity comfort. So you see this S235 region and S235 AB region. So they are connected by this intermediate emission. It's called bead-like structure. So such bead-like structure is often explained under the signature of the collision or interaction of the cloud. So in this two S35A AP and S235.
Мы его теряем. Серьезно. Напиши, что вас включил камеру, я тебе говорю, так меньше будет.
Do you know the end?
He's gone.
It's only summary left.
Никита, что ты делаешь?
Ну, я показываю, что будет дальше.
Пацан, потерял. Что? Потерял пацан. У нас вообще отлично.
Все.
Hello? Anybody here?
The speaker is bugging.
Они там вместе сидят.
Интернет есть.
Okay, anyhow, so we see the summary, yeah? Maybe there are some questions, so we can type questions to him.
Sure.
Are there some questions?
Questions to you.
Why for me? To the vendor? Yeah, for me, yeah. I know almost all of these things.
I think so.
Except for H2 emissions.
Very overlap.
Which you don't know, so you can ask questions.
Hi, did you hear us?
Anyhow, does anybody have any questions to type? Sasha, do you have questions?
There was a position velocity diagram.
Yeah.
In one diagram, there was drop towards bottom, on another towards top. This shift was on the bubble, and there was also final position velocity diagram, which shown bubble.
No, this was from ours, from the other paper. This was from the other paper, devoted to another object by other authors.
Так, секундочку, мне нужно пару минут, чтобы бросить его нашу ссылочку на YouTube.
Там задержка будет, минут почти.
Зачем? Зачем? Потому что он хоть как-то нас слышал. Чтобы ты...
Нет, скайп все запись.
Нет.
Скайп не работает. Отлично. Секундочку.
Сейчас вторая презентация нужна.
Она прямо сейчас будет по скайпу?
Да.
Замечательно.
От того, который
у нас
там
не
слева выглядывал.
Видишь?
Может, сделаем
YouTube broadcast. Questions. Okay.
No questions.
No questions? Really?
have
Serious
to
maybe
again
questions,
focus.
but comment.
Yeah. Comment.
So, no, sorry. Do you have any comment?
When you consider the feedback, one of the feedbacks as the H2 region seems to be not very efficient for the propagation of star formation.
Wow.
Because the degree of compression on the shock wave by shock wave induced by H2 region is not high.
No. Let him say.
Okay.
Not type. Don't type. Yeah.
Yes, I see that, of course, the shock waves induced by supernova are efficient. Sometimes the radiative implosion, what was considered also is important, but I somewhat doubt about the efficiency of H2 region as a driver for the sequential star formation.
Trigger.
From my
Sequential is different. Trigger.
Sequential, yes, but trigger is not formation.
These are different things.
When you put all together, it is the same what was said here as so-called compilation of matter by H2 region. It's not efficient for star formation.
Yeah, for high mass star formation, this collect and collapse scenario. Just look, they say that it takes place. Yeah, it's papers by Zabagnon and Darwin. It's a number of objects.
Complex area. I followed your talk also, this talk, how you try to separate one mechanism, one feedback from other. But I think that we should have a lot of doubts. Scientific doubts about.
Yeah. Just read the papers.
So this kind of feedback mechanisms are actually happening in a very small scale. Cannot be beyond 10 or 20 parsecs.
It's my general comment for several talks, especially for Andre and for this one.
Actually, the radiation-driven explosions have been seen on bright clouds, but as you said, it's very difficult to separate out what is triggered and what is
like here.
So what you need is basically to find out the ages of the young stars, and you see the age gradient. If you have these kind of proofs, then only you can say it is triggered. So there are few cases where you can do that, but not you can generalize.
Мы сейчас только наговорили, вы все стерли, да?
Нет, ну я просто...
There is one more suggestion, because we lost connection, yeah? So, no, sorry. My suggestion is that Lev will make a presentation now why the connection is established again.
He says that cloud is a new progress integrated in our work apart from sea.
Yeah, collected collapse and the radiative drive in explosion. Yeah. Yeah. He says that cloud-cloud collision is investigated here. So cloud-cloud collision was suggested by Evans in 1985 for this region. Okay. So now before the connection is how to say is established again, just let's hear left or. Another suggestion is that we can have a coffee break now.
У вас флешка с собой с презентацией?
Флешка со мной, а так все, потеряно уже все?
It's about 15 minutes. Before coffee break, so maybe better to go to have a coffee break.
Yes,
they will.
By the time we come back and do that.
Давай пойдем кофе попьем, а потом все.
Я просто скажу пока.
Проверю, если готовы.
Ага, проверь, потому что видишь, ты мало времени.
Мини-кардинальное решение есть?
Тут все рассказал. Да, Игорь, ты все рассказал, на самом деле. И название такое.
Ладно.
Мне не важно.
Нет, сейчас расскажу.
Я ставлю.
Пойдем.
Пока что.
Yeah, let's go.
Так,
Да,
так,
здесь
ну,
вопрос. Там ниже
Петя. Ну чего, фокус настроить. Каким образом? Тут механически крутить нечего?
Нет, там автофокус должен быть, он никогда не работает. Я думаю, нужно поменять расстояние между камерой и... Так, давайте по порядку.
Вот оставь пока, как есть.
Дело не в этом,
через
нам
недельку, две
надо,
будет.
короче, Linux удалить, я же сказал.
Никит, молчи, пожалуйста, и давай конструктивное предложение.
Нашел документы, паспорт давай, и вот там, где репорт один.
Так.
PDF?
Нет.
Прозрело?
Да. Что ж, PDF?
Ну, переведи его сам.
Давайте поближе поставим.
Куда поближе?
Я сам займусь.
Ну ладно, тогда я просто беспокоюсь, что там...
Петя, а у тебя наушники с микрофоном?
Ближе,
Да,
ближе.
но они не пойдут через этот разъем.
У меня наушники с микрофоном надо?
Хороший
Да.
микрофон?
Да.
Там микрофон отдельным разъемом, Никит.
У меня микрофон отдельно разъем. Что ты говоришь?
Нет.
Надо, нет?
Ну, по крайней мере...
Или мы можем вот это включить, слышь?
Что там?
Если идет 3,5 выход, мы можем вот тот микрофон подключить, это нормально будет, или будет страшно.
Да какая разница? Проблема-то не в микрофоне. Проблема в отсутствии звука. Так.
Да. Да. Заслушай, то же самое.
Да уж.
Да. Нет, тут лишнего говорить не надо, потому что Роскосмос купил себя крайне неприлично. Ну, вы же помните, обещали все вернуть, нифига. Ну, вот так я в этом же духе был. Хорошо. Хорошо. Я здесь первый доклад слышал по... Ну, собственно, меня это сильно и привлекло сюда. По УВИН. То есть по фасаду. Копию сделал, привезу. Результаты, да, скромные, там, но тем не менее, фотографии в стиле Галлекса. Хорошо, так что. Хорошо, Миш, тогда счастливо. До прокуратуры.
Так-то.
Поехали сказать.
Сейчас председатель, с трансляцией ты ее оставил?
Нет, сейчас стримит. Нормально.
Ребята, мы очень извиняемся за косяки с трансляцией. Ну, в общем, такие дела. Стримить на ветку — это ужасно. Просто не представляете как.
Оль, попроси, пожалуйста, Игорь Иванович связаться со следующим докладчиком. Попроси, пожалуйста, Игорь Иванович связаться со следующим докладчиком по скайпу.
По скайпу.
Да, стоп. И?
Ты угораешь?
Это Игорь Иванович.
Так, теперь берем. Тест Pro, где тест Pro?
Мне кажется, в каждом микрофон нужно.
Вас приветствует служба тестирования связи Skype. После сигнала начнется запись вашего сообщения длительностью до 10 секунд. Затем вы сможете прослушать свою запись.
Can you feel the love? Can you feel the love? Так, и чё? Видимо...
Если вы слышали свой голос, значит настроили Skype правильно. Если же вы слышите это сообщение, но не слышали свою запись, то настройка записи звука выполнена неправильно. Проверьте свой микрофон и его настройки или обратитесь на веб-сайт skype.com для получения дополнительной помощи. Благодарим вас за использование службы тестирования связи Skype. Всего
Попросите
хорошего.
их, первое, не использовать видео, потому что бесполезно, зачем нам смотреть на человека. Второе, если у них есть наушники с микрофоном или просто микрофон, то пускай они его лучше ставят, потому что звук еще искажается из-за того, что они говорят в ноутбуковский микрофон.
У меня не соединяется.
Так и значит, у них проблемы со связью все-таки?
Я не знаю, у меня и раньше не соединялся. Вот у вас соединялся, но что-то не нравится.
А вы перезапустили скайп?
А зачем?
Это ж Mac.
И что?
Могут быть веселухи. Это ж скайп, точнее, вот, не Mac. Ну, может перезапустить скайп, потом попробовать.
Ну, попробуй.
Значит, хотите?
Да.
Не хочешь?
Оль, твой ноутбук официально прокачан. Еще и изнасиловал.
В смысле, ты говоришь, что там Linux надо менять, да?
Нет, там нужно не Linux, а просто нужно поставить GNOME.
Что это такое?
Оболочка.
Думаешь, проблема в оболочке?
Петь, вот у тебя такая стоит, да?
Да.
И у меня такая же. Вот, Игорь Иванович, вы зашли в скайп.
Ну, я перезапустил просто.
Ну вот я вам говорю, мне сейчас скайп сказал, что вы зашли в скайп.
Слушай, я не могу связаться. Он пытается дозвонить.
Может, он вообще
Оу,
его
оу.
компьютер?
Нет, он показывает зеленый.
Оу, оу. А вот он нет микрофон включает, тот разница.
Какая разница?
Ну как не выцепляется?
Встаньте, постучите по камере. Не по
Готовы?
этой, вот по этой. Да, все. Не лупите.
Тестирование связи Skype. После сигнала начнется запись вашего сообщения длительностью до...
Вот это вот работает.
Я уже закончил.
Да, в общем-то, да, уже вопросы. Можно вопросы задавать.
Муж наложились.
Так, он вот написал следующее, что в случае технической проблемы я он попросил профессора Отшку, значит, показать слайды, где он коллаборатор.
Ручка. Здесь вот принтер. USB отлично.
больше не помню ничего.
Сорокапятилетней давности анекдот. Там где-то в Иркутске приехала японская делегация на завод, и говорит: подождите, сейчас директор с Москвой разговаривает. Да. И вот они слышат крики: Москва! Москва! Ты меня слышишь? А они спрашивают: почему он так кричит? Он с Москвой разговаривает. А по телефону он не пробовал. Такая аналогия.
Ну, что он предлагает, вот, чтобы это, связано с вами?
Пока у нас время есть, я стараюсь подготовить, тем более, что другие докладчики, чтобы...
High Special Resolution, да? Трудно сказать. High Special. Какой будет? Высокое разрешение? Можно? Ну, вот по этому докладу. Massive Course. Они все в группе. Можно разделять? Довольно хорошо.
У меня это результаты однозеркальных наблюдений, так что тут все поставлено. Тут все поставлено. Да, я ничем удивлять не буду.
Вас приветствует служба тестирования связи Skype.
Все тихо.
После сигнала
После сигналов моем.
длительностью до 10 секунд. Затем вы сможете прослушать свою запись.
В офисе Skype отложили пару личинок.
Голоса
я не слышал. Нет, там были названия поняли немного.
Но не слышали свою запись, то настройка записи звука выполнена неправильно. Проверьте свою запись.
Да мы рассказываем, у нас уже записано, вот он и
На стриме есть, на стриме.
Аудио.
Обратите внимание на Ярослава, он вообще птичек гладил и играл в игру.
Спасибо.
Ярослав тоже был. Телефон владел. Я ему говорю, убери, а он что?
Так, я боюсь эту штуку сломать.
Ты вот сюда вот смотри, куда крутишь. Вот сюда вот, вот сюда вот.
Ее не крутить надо, ее надо наклонить.
Вижу.
Право наклонять. Вообще надо вот так сделать, наверное.
Я не понимаю. Правильно, нет?
Да, ну сейчас с тобой будет это.
Левую еще.
Сейчас кто будет докладывать, слева или скайп следующий?
Если будет скайп, то скайп еще.
Скайп?
Все зависит от Андрея Михайловича.
Андрей Михайлович, кто будет следующий, Евгений или скайп?
Так если скайп недоступен, так значит Евгений.
Ну, оно будет так иначе крут, потому что не по центру расположил его.
Что?
Да, скайп готов.
Человек готов, да?
Скайп готов.
Ты попробуй позвонить ему сначала.
В русском языке слово «готов» должно быть многозначно. Готов.
Уноси готовить.
У него есть презентация вторая следующая?
Ну вот я не понимаю. Что? Слева у нас.
Ну там задержка. Пока уйдет в Google, пока вернется в Google.
А в чем разница между левым и правым?
Правый это то.
Так, вы смогли с ним связаться?
Сейчас мы ему позвоним.
Сейчас мы тестовый звонок ему сделаем.
То есть слева это то, что сейчас на YouTube. Право это то, что...
Hello, did you hear us? Okay.
Do you hear? Can you hear?
Микрофон есть, камера.
Есть, да.
Они меня не слышат.
Hello? Can you hear us?
Yes.
Oh, that's good. Now we in break. Может, вы расскажете?
No, we will start in 1 minute.
Давайте все.
Мне вот точно буду знать, когда я обманываю.
Всегда.
Это правда.
So let's start.
Включайте камеру не обязательно. Она вполне неплохо слышит.
Спросите, все нормально, он видит все. Он готов.
Are you ready to start?
Пам-пам-пам. Это уже что-то у них, видимо. Уже.
Давайте через свой мобильник попробуем.
Ну вот.
Связаться через мобильник и подключить к колонкам. Его будет слышно, без презентации он увидит.
Нет, это у нас проблема.
Бюджет на этом закончится.
Нет, почему? Я трачу много, говорю, 4G включить, да и все.
Hello? Hello? Okay.
Видео включи.
Видео.
Okay, let's start.
Видео, сейчас.
It's one of the isogel fields which Professor Oja also was quite keenly involved. Next slide. Yeah. So of course we all know the challenges which face us in understanding the Milky Way. In that we are within the plane of the galaxy, and there is a large and uncertain extinction in the line of sight, and there's a uncertainty in the distance, and most of the fields, especially in the galactic plane, they are quite crowded, and you have a mix of stellar populations with overlap occurring in the same line of sight and at different distances, which causes a lot of confusion. Okay, so in this next slide, please.
Да ё-моё. Нет, не может.
Он отрубился. Он не в сети.
Ё-моё. Hello?
Hello.
Yeah, it seems that we have a trouble in connection both on our now on your side.
Hello. Yes, I can hear.
I think we can continue.
Okay.
Видео.
Okay. So I cannot see the slide, but I'm assuming that it's saying about the infrared surveys. Okay?
Yeah. Я включил, оно не включается. Окей. Да. Окей.
Ты чего?
Что я сделал? Видео.
Не знаешь, что делать, просто выключай.
Нет, перезвонить надо, раз видео никогда не передает.
У тебя видео не работает вообще.
Чаще по скайпу делал.
Okay, I think Dmitry, can you give a presentation because we have technical troubles and
We have not gone through a slide actually, so not.
Hello? Did you hear us?
Hello?
Yeah. Everything fine.
Yes. Okay, fine. Now I can see the slide as well. So maybe we can go to the next slide. Okay?
Next.
Maybe we can jump 3 slides from here because we are running short of time. We can as well skip a few slides. Yeah, next one. Okay, so the work that I'm trying to present here is basically reported in this paper. It's a relatively old paper, but I thought that it would be more interesting to discuss this in this seminar because it might be of interest going further for a collaborative program. Okay, can we go to the next one? So in this case, in the Milky Way, we have been studying this with Professor Oja and several other collaborators within India as well as from France and elsewhere. And so some of the regions have been explored in quite detail. And one such direction is tangential to the scutum crux arm, and that is shown in this slide. So this is the towards L equal to minus 45 degrees, and it's across the galactic plane. So can we go to the next slide? Yes. So here we show you a color composite of the infrared space observatory image at 7 and 15 micron, and the caption explains everything over there. And the connection between this region and the topic of this seminar is that we have marked here some of the very few young stellar objects which were identified as part of this survey. So these are marked by blue squares which are listed, which are pointed in most of the extended emission regions. Okay, the next one. Yeah. So in this paper we had published, actually we had compiled and cross-identified nearly 740 stars detected at 7 and or 15 micron, and we had added the counterparts from GLIMS, TUMAS, DENIS and MSX. Okay? And this catalog is now on CBS, and we had done this cross-identification by hand, looking at each of the 746 stars. The next slide. And yeah, so this is the page on CBS where you can get the catalog. And the next slide will show you further details about the catalog itself. What are the different columns are sample sources in each. Next slide. Okay. So here we see examples of 3 different types of sources which were listed in the catalog. And yeah, in the association flag, this tells you about the how good the association is with respect to different surveys. Okay, and how and the quality of the data. Okay, so sources which are very secure associations are of the of type 5, and these are definitely well identified sources, and we can. We're running short of time now. And next slide, please. Yeah. So what we started with in order to study the stellar population here is to look at the J minus K versus J diagram. And if you see this is for the whole field of 1 degree by 20 arc minute, 1 degree across latitude and 20 arc minutes in longitude, okay, galactic plane. And different types of sources with different identifications are shown in the with different symbols. And if you see the mess that is there, it's a very complex color magnitude diagram with a lot of things all over the place. Okay. So if you go to the next slide. Next one. This shows basically the J minus K versus J diagram using the MSX and now the ISO gap is 15 micron. The next one will show you 7. Next. 7, and then you have also the glimpse and then the 2 mass detections. So the black dots are entirely 2 mass detection, all the 2 mass detection. The red dots are the ones which have 2 mass detections, of course, but also detected in the glimpse data set, and then so on. Okay, so it shows that different surveys have different levels of completeness, and one needs to take into account all these different effects when trying to understand the whole line of sight, whatever is the stellar population is there. Now, if you go to the next slide, we'll discuss how we use the red clump locus in the J versus J minus K color magnitude diagram. The next slide, please. Yes. So here we have just shown you the kind of color, the red clump locus expected for 2 different directions within the field, okay, within the LN45 field, and one panel on the left shows you the close to the galactic plane, that is at B equal to 0, okay, a small patch, and it shows that here the extinction is so the last dot which you have, and whereas if you go slightly away from the galactic plane, go towards plus 0.5, then the extinction is relatively reduced and one can go to higher longer distances. Okay, the next slide. Yes, so here we have summarized the entire plane into 10 different 9-10 different sections, and it shows you how the different parameters vary as a function of the location in the field. Okay, so the various columns are listed here, and I think they are self-evident. We can probably discuss it further if need be. If you go to the next one, so this is a map of is just a plot of the figures in the next slide, please. Yeah. So in this we have the distance as a function of galactic latitude, and it shows that how the color magnitude diagram is restricted to shorter distances at as you go closer to the galactic plane, B equal to 0. Okay, and the same thing is for the on the right side you have the extinction values from our work as well as from the Besançon model and other CO data survey data as well. Okay. The next slide. So using the red clump locus, we had actually estimated the distance and extinction values for each of the individual stars, assuming them to be red giant stars, and assuming the red clump locus to constitute mostly K2 type giants. Now, in this particular field, we really do not know the extinction coefficients at longer wavelengths, and this was also a work which was done to determine what is the extinction coefficient at 7-15 micron as well as the glimpse bands. And this color diagram shows you the details of the field, okay, used to determine the extinction coefficients, which are listed in the table just below the panels. If you can go to the next slide. Next slide. Yeah, so we made use of these the extinction values as well as the distances to set up the bolometric luminosity color diagrams and extinction corrected and distance corrected, and those are shown in the K bolometric magnitude K band versus K by 15 extinction color and corrected, and this shows you the highly mass losing AGB stars at the top with bolometric magnitudes brighter than -7, and in between you have 8 mass red giants and then of course fainter objects right at the bottom, but those are very few in number. It shows you objects which have color excess at 15 micron, indicating that there is a big excess in magnitude, excess in reddening, which is an indication of that. If you can go to the next slide. Next. Yeah. So using these color magnitude and color diagrams, we are also able to identify several YSO candidates. And if you see the details here, because we used only the red lump magnitudes to estimate the distance and extinction, we are really not sure about the YSO candidate distances and extinction values. And this is probably some work which we can start up for the entire ISO. Next slide. Okay. So in this, we have shown you the color diagrams from UMAS and ISO, as well as color magnitude diagrams, and the objects which have the nexus compared to the red giant locus, red giant extinction locus, is they are marked with the blue squares. Okay, and we just follow the estimate in different directions. Now, if you look at the next slide, this is the glimpse color and color magnitude diagram, and the red box in the color diagram from glimpse is the location of the class 2 YSO. Okay, and we see that most of the objects with large color excess, with excess reddening, are basically of this class 2 type, and they are mostly associated with the location of the extended emission regions in the image which I had shown in the beginning. Okay, similarly on the right side you have the color magnitude diagram again from glimpse, and it very clearly shows the excess. So these are diagrams which can be used as diagnostic measures to identify the M-stellar object populations in different directions, and a similar work should be carried out to get a full a census of the M-stellar population over the entire disk of the Milky Way until whatever can be probed. So if you can go to the next slide, I'll just summarize this. Yeah. So we have basically established a scheme for the analysis of Milky Way stellar population data, and further this needs to be taken further using the newer data set coming in online. So I'll just conclude with the thanks. Next slide. Yeah. So this shows you the location of our observatory with the star trails, and thanks for.
Any questions, anyone? Are there any questions?
Audio is not clear.
Okay.
Yeah.
So let's.
I'm not able to hear any questions. So video is, but audio is not coming through, it seems.
Okay. So
maybe you type. If there are any questions.
Type what? So
Okay, thank you.
Thank you for. Thank you. Goodbye. So next speaker.
Как назвать правильно сообщение? Так вот. Как по-английски? Так вот.
Yeah. Yeah. Are you ready? Okay. So let's start.
Okay. Good afternoon, everybody. So first of all, I want to thank Dr. Igor Zinchenko to invite us here to deliver this talk. So I'll be talking about multi-wavelength study of mid-infrared galactic bubbles. So these are my collaborators, and okay, the brief outline of my talk is, first I will describe about what is the role of massive stars on parent molecular clouds, then why do you need to study the galactic bubbles, and why do you need to study them in multi-wavelength, and finally I will end up with two brief examples. Means I will not describe all the details of the study of these two galactic bubbles, but I will brief some main result of those studies, and finally I will conclude. Okay, role of massive stars, as you have Locas was already given the introduction, and also yesterday Maria has also given. So they play important role on the evolutionary wind, strong UV radiation, and also supernova. They finally end up with supernova explosion, etc. So but in spite of their importance, formation and evolution mechanism are still debatable. They can play constructive role by giving feedback, and by that feedback they can trigger next generation star formation, or destructive role in terms of they can disperse the material into ISM. But whether they can trigger next generation star formation or they disperse the surrounding material into ISM, such direct observations are very rare. So, but the interesting things come up here, that many of the galactic bubbles which are seen in Spitzer glimpse images, 8 micron images, are found to be associated with massive stars. So what is before going to the details that why do we need to study them, I just want to introduce them, that what are the galactic bubbles. So these mid-infrared galactic bubbles are small scale cell or ring-like structures seen in Spitzer glimpse 8 micron images. So objects that could produce are OB stars, ultra-red stars, open cluster, or supernova explosions. So this is one typical example image of a galactic bubble. So you can see a complete circle-like, ring-like structure here. But life is not always as easy as we expect. So there can be several kind of morphology, like it can be broken, it can be bipolar, it can be tripolar, it can be multipolar, or different irregular shape of morphology. So that tells us that this kind of structure can only form when several energetic sources are embedded there, which are acting to in this molecular cloud to shape up, bring up those shapes. So now I am going to why do we need to study those bubbles. This why do we need to study those bubbles is as Churchill et al. Who reported those mid-infrared galactic bubbles, they concluded that 25% of the bubbles overlap with known H2 regions, which are generally developed by OB stars. So, and several other conclusions are there, so I am not going into the detail of those, but I want to concentrate particularly this conclusion. So in this 25% bubble give us the region to study the impact of massive stars on their surrounding bubbles, because they are associated with H2 regions. But why do we need to study them in multi-wavelength? Because if we want to study the overall region, we need to know the ingredients of that. And here we cannot just like cake, we cannot taste all the ingredients. Only information we have light. So different wavelength will give up different information of the region. So that's why we need to study them in multi-wavelength. And in star forming region, like if we have optical and near infrared imaging data, point source catalog, we can characterize sources, and we can also measure the distance to the region. If we have near infrared and mid infrared data, imaging data, we can identify young stellar populations by color magnitude diagrams. Mid infrared and far infrared data will help us to map the hot and cold gas regions. Also, radio continuum data will help us to map the ionized region. Then in addition, if we have CO line data, that will help us to understand how the molecular gas is located or how they are oriented in the line of sight. All those information you can get from the CO line data. And in addition, if you have polarization data, that will help us to understand the orientation of matter, how they are distributed, and also the magnetic field. So with such introduction, I want to now go to the example study. First one is the one bubble M46, which is associated with Wolf-Rayet star. I just want to mention here that in Churchill conclusion, it was they never found a Wolf-Rayet star associated with a bubble. But we took up this project. We matched the the available Wolf-Rayet star catalog with the bubble catalog, and we found that at least 10 of them could be associated with Wolf-Rayet star. And here I am presenting the first study of such bubble associated with Wolf-Rayet star. So this is the region. This is M46 bubble here, and this is the location of Wolf-Rayet star. It is located about 18 hours and -5 degree of depth and about 5 kiloparsec of distance. You can see several structures are there, and here on methanol measure 6.67 gigahertz methanol measure source is also located there. But okay, we have the region, we know the Wolf-Rayet star is located, but we need to properly characterize the Wolf-Rayet star located there. So that's why we obtained the spectra of the Wolf-Rayet star using 2-meter Himalayan Chandra telescope, using the optical spectra as well as near infrared spectra using our own instrument T-spec. So this is the spectra of that region, Wolf-Rayet star. You can see several broad emission lines which are generally expected from Wolf-Rayet star. So we use those lines to identify what kind of source it is and what is the velocity those wind velocity of the Wolf-Rayet star, and we found that it is a WN7 Wolf-Rayet star and has wind velocity of about 1600 km per second. Okay, now we have identified the main source towards the region. Now we will look at the surroundings. So what is happening surroundings? To know that what is the status of the molecular clouds or cold gas over there, we generated the column density map using Herschel images 160 micron to 500 micron, and we did pixel to pixel gray body modeling to generate the column density map. So here is the column density map. You can see several cold condensation are seen surrounding the Wolf-Rayet star. Here is the location of the Wolf-Rayet star, and you can see many cold clumps are seen towards the region. So again, similarly as Lokesh described the schemes how to identify young stellar sources, we have also identified YSOs, and here YSO, and of those YSOs we have generated the surface density map of those YSOs, and these red contours actually show the surface density map of the YSO, and the blue contours, cyan contours, is the velocity integrated 13CO map of the region. You can see several, those YSOs are mainly clustered in the cold clumps. These are the cold clumps as also seen in the 13CO map. So this indicates that there could be the influence of that Wolf-Rayet star which is helping the accumulation of cold clumps as well as the formation of those young sources. So, but which is the dominant factor of that particular Wolf-Rayet star? What kind of pressure it is exhibited on the surrounding material? To measure that, we have calculated the different wind pressure budget from that particular Wolf-Rayet star at a distance of about 2%. So, and we found that the wind pressure from the Wolf-Rayet star is the most dominant factor here. So then we finally concluded, okay, as I mentioned, I'm not going every detail of the study, but finally after verifying many other things, we finally concluded that the strong bubble is mainly developed because of the strong wind from the Wolf-Rayet star, and it has also influenced the molecular condensation and also might have triggered the formation of next generation star in the surrounding molecular cloud. So the details of the work is presented in this paper. On interest, you can find more detail about it. Now I will move to the next source. So this is associated with OB star, different from the previous one. Here is the bubble, broken bubble-like feature. You can see clearly visible. This region is associated with an infrared dark cloud and also with a pillar-like structure. This interesting feature of this interesting point noted of these pillars are generally known as the site of Tigger star formation, and they are generally point towards the massive stars. It is observational fact. So this region is located at about similar array deck and but nearby distance of 3 kiloparsec. So, but for this region, we only know that there is a presence of ionized region. This is 20 centimeter radio continuum map, this red contours. But we need to first identify the ionizing source of that region. So for that, we use photometric scheme to near infrared photometric scheme to identify the probable OB star which could be responsible for this ionization of this region. To develop that H2 region. So we found, using photometric scheme, we found 7 potential targets, and we could perform spectroscopy of 2 of them, this marked by this blue star here, because other sources we could not do because they are beyond our spectroscopic capability using 2-meter Himalayan Chandra telescope. They are fainter than our limit. And this is the spectra of those 2 stars. Here you can see several hydrogen lines and helium lines are present in both the spectra. So, and we matched these 2 spectra using the online available spectral catalog of pickles, fruits, and we finally concluded, after matching we concluded that this source is corresponding to O9 type source and this is B0 type source. And we also estimated the Lyman continuum flux required to ionize that, to develop that H2 region, and which corresponds to that. It should be a O9 type star, and here you can see I have shown that this is the O9 type star which is located near to the peak. So this is the main ionizing source of that region. Now similarly we have tried to identify what is the pressure budget which is responsible in that region. So here you can see radiation pressure and pressure due to the ionized region is almost equivalent. But when we looked at this 2.12 micron H2 band image, continuum subtracted H2 band image, you can this H2 emission is mainly occurred because of soft region. When the cold material is soft point is developed at the interface of cold and hot gas. So in that soft region, this emission is occurred, and you can see this is actually inverted image. So that's why it is in black. So this periphery of the H2 emission is exactly matching with the bubble periphery. So that indirectly tells us that the pressure due to H2 region is the dominant factor here. So we're mostly influenced by the expansion of the H2 region. Similarly, we developed as I presented for the earlier sources, we developed the column density map, and also we have identified OISO and developed the OISO surface density contours here. So here also we found that this several condensation are seen surrounding the OB stars, and also OISOs are clustered around them. Now we try to quantify whether these young sources are mainly developed because of that ionizing feedback of the massive stars. So for that we did the ACD modeling of about 80 YSOs to determine their age. We used the online available ACD filter tool of Robitali et al. And then we determined the mean age of YSOs in several parts of this region. So you can see that age of YSOs in different parts are almost turn out to be similar. So that means if H2 region, expansion of H2 region, it could have been the triggering source, then YSO, mean age of YSO in this part and this part could have been much lower. But they are turn out to be similar, and with error bar they are almost same. Okay, and age distribution is shown in the cumulative distribution plot here. There hardly any difference is seen in the age distribution here of these three parts of OSO, means OSO in these three parts of the cloud. But, and also we try to determine the dynamical age of the H2 region. This dynamical age means that up from the storm gain radius, the time it takes to reach the density equilibrium point. So that dynamical age is also about 0.7 million year, which is also comparable to this YSOS. So that means the expansion of H2 region could not be the main driving source of, or it is not triggering the formation of those YSOs. So we have to look for some alternative. So for that we looked at the channel map of 13 CO data, and we found that there are two molecular clouds present towards this region. One is at a velocity range of 37 to 43 km per second from the here to this map, and another one is present at 43 to 48 km per second velocity range. Okay, now we developed the made the position velocity diagram of that region for a velocity range from 37 to 48 km per second. This is the velocity integrated map, and here is the position velocity diagram. So here you can see, as Lokesh also mentioned, that this broad bridge-like structure is seen. Probably it is not clearly visible here, but here you can see the two peaks are clearly visible. At one is around 45 km per second and one is about 40 km per second. Here also you can see similar, and they are joined with a broad low intensity broad bridge-like feature, so which is indicative of the interaction between two clouds or collision between two clouds. So similar phenomena is also seen in this RCW 120 by Tori et al. In 2015, and they elaborate that how a cloud-cloud collision can make a large cavity, and that condensed matter here can form can give a favorable condition to form high mass stars, and then from that UV radiation from that high mass star can fill up the cavity, and this will end up with a broken bubble-like feature with ionized emission inside it. So which is exactly seen in the case of N37 bubble. You have seen that there is a broken bubble-like feature, and it is filled up with the ionized radiation. So from here we have concluded that this here cloud-cloud collision might have taking place, and that has produced that massive OB star, as well as we have no evidence for triggered star formation on the surrounding molecular cloud by the expansion of the ionized gas, but they could be produced because of those same cloud-cloud collision phenomena. So the details is available in this particular paper. So now I'll move to the summary, whatever I have presented. So detailed multi-wavelength study of these two galactic bubbles. So different star formation scenario here. Though we have seen that there are substantial influence of massive star on their surroundings to develop those bubbles, but it always requires some thorough detailed multi-wavelength study to specifically characterize the star formation in this particular region. So that is my conclusion, and that's why we have chosen several other bubbles to study, and we are following them up in multi-wavelength using GMRT, using Himalayan Chandra telescope, and also available online multi-wavelength data. So that is the thank you.
So questions?
May I ask, how did you derive the values for wind pressure, for radiation pressure and gas pressure?
Actually, a formula are available, theoretical formula. There we have taken for radiation pressure, have taken the luminosity because we know the spectral class of the source. So from the luminosity, how much it needs to at particular distance, because we have calculated at about 2 per sec or sometimes it is 1 per sec. So how much pressure, radiation pressure it is needed.
Yeah, but radiation pressure could affect on gas and dust. So you have to know the property of dust, for example, in this region, since the radiation pressure acts to the dust.
Yes.
And dust transfer the energy to the gas. So you should know.
For that, we have taken that dust to dust ratio of 1:100, that kind of thing.
No, you didn't take into account the relative pressure at all.
No.
Yeah. So the question is that the intensity of wind, it's kind of parameter that it differs. The mass loss rate, the velocity is more or less understandable, but, the rate mass loss, that's intensity of wind. How do you introduce this parameter?
Mass loss rate and
10 to the minus 6, 10 to the minus 7.
Oh, that we have derived from this from our observed spectra only. It was
from spectra.
Yes.
Okay.
Yeah. We have derived because I have not shown every detail of this study. So if you want to know, I can
what is your estimate? Probably is this the relative velocity of two colliding clouds. What is the relative velocity?
As proposed by this Foucault group and all, it is about 10 km per second or 10 to 20 km per second.
10 to 20.
In your case?
In this case, of course.
Yes, in this process.
Because Foucault case is applicable to formation of clusters. Which clusters?
Yes.
Not like this.
But their theory is also, because this paper I have shown for RCW 120, that is Foucault group's paper only, and they have shown how that was 4 type star.
I know this.
Yeah, so just one more question. Do you think that this cloud collision is the common scenario for such infrared bubbles, or it's just one of the possibilities?
Here I have given 2 examples, and 2 are different actually. So actually we have taken up that project, another project we are looking for. So whatever such data is available, CO data, we are trying to derive the position velocity diagram to look for such signatures, whether cloud collision is another effective phenomenon or triggering star formation mechanism. So to look for such
sample is very small actually. So I mean only very few bubbles have been studied thoroughly. So out of these big small sample, only 2 have thoroughly studied. So we don't know. This one, I mean, chance coincidence that one of them turn out to be possible. But they may
Actually, both are first kind of study. Means one is with Wolf-Rayet star, that is also the first study with Wolf-Rayet star, and where cloud collision is found in bubble, that is also kind of first study.
Any more questions?
Not exactly the question. It's mostly can be qualified as a comment that for some last decades I have seen the term bubbles applied for many structures. First was the hot bubbles produced by supernovae. They are large enough. Some of them are super bubbles, hundreds of parsecs, and tens of parsecs is the hot bubble. Now you deliver new bubbles which are produced of different nature.
Yes.
So that I think that this ambiguity should be somewhat excluded. We should maybe to have some kind of notification of these various bubbles. Otherwise, each time when we see bubble, anybody will imagine own object.
Yes. Actually, it happened also. When I mentioned bubble, they thought that galactic scale bubble, super bubble. So then I told that it is mid-infrared bubble, which is about parsec scale, not the mega parsec or sorry hundreds of parsec scale. So
maybe we need to introduce some
nomenclature.
classification of bubbles.
Yes.
Okay, any more questions? So in this cloud-cloud collision, what about the velocity of the star? The ionizing star itself. What should be its velocity? If you compare it with the rest of the molecular gas, you can draw a conclusion. Because the colliding cloud should move with the same velocity as the ionizing star of the ionizing region. So it should have different velocity than the ambient gas. You can measure this and see your spectra.
Actually, here the ionizing star is only produced after the collision.
Yeah.
What? Yes, but it moves with the parallel gas.
There might be some residual velocity present. Okay, that I will try.
No, it should move with the velocity of the
No,
parallel gas.
this is the collision, the pressure. So
Yes.
this is two pressure supported clouds.
Just
Where is the star you are mentioning now?
this is small cloud,
Yes.
which is moving toward this, yes? And so this star is situated in the small cloud, and it should move with the velocity of the small cloud.
Okay. If the velocity of collision is on the level of 10 km per second,
Okay.
it's between 0 and 10.
Yeah, but you can measure this.
Yes.
You can really
There
measure this.
might be or might not be some residual velocity for that ionizing.
It's not residual. You cannot stop the star. If the star starts motion, yeah, you will not stop it with the cloud. It will move with the same velocity.
No, but you can stop cloud.
No, cloud will be stopped, but not the star.
No.
No, but the star is forming from the cloud.
From stopped cloud.
Right.
Yes, so it will move with the velocity of the cloud. So in this case, you will have
Stopped cloud has 0 velocity.
no. Why? The star comes from here. Yes.
No, there is not there.
But it is
Here
formed.
later. Exactly. When the
Star
cloud
is only forming after the collision.
Yes.
After collision,
It's
yes.
not an initial star. It's just the result of.
If there is an initial star, it can
Okay,
be
so
stored.
the time scales and other things. It's
Yeah, if you have massive star moving the same velocity to already will destroying the smaller ones, you can't have this kind of scenario.
okay, good. So thank you. So next speaker.
Sequence of the Hello, everybody. So I'll try to be not to be long. So the title of my presentation is quite similar as the few presentations you have heard before, multi-frequency studies of massive cores. But there is some difference that this is differences in a term course. So that's why I will now go deeply into some large-scale morphologies or small-scale structure of such a kind, and limit myself to the structure of the sizes of the core, about tens of parsons. So this work was done with collaboration with our colleagues from Institute of Radioastronomy from Kharkov, and also from Onslow Space Observatory. Okay, I would like to begin with a slide, with such slide where 22-meter radio telescope of Crimea, situated in Crimea, is shown. So some lyrical introduction. So about 30 years ago, I started my activity, radioastronomical activity at that place. At that moment, we do not use this
this instrument for observation, but our Ukrainian colleagues from Kharkov still used it till now, practically till nowadays, and during several years they observed the position of methanol masers by this telescope in some molecular lines in 3 mm wavelength range, especially HCN 120 line, and only in one position, and they showed their results as a profile which shows some very large deviations from purely Gaussian profiles, with absorption dips, with multiple components, with high velocity wings, and so on. And together with them, in the framework of our mutual, our joint grant, we tried to select some object from their database, and to make a proposal for the further investigation, for the further studies of selected regions, to make maps. First of all, in this HCN and H13CN, the first goal was further make modeling of the sources, which is more or less spherically symmetric, and to see what we could derive from this non-Gaussian profile, because you see that HCN is a rather complicated molecule for modeling. It's even in the case of a purely Gaussian profile, the so-called anomalies of intensities of hyperfine components is you need to make non-LTE models, non-LTE calculations for to explain such things. So, and the other goal of other project was to see also chemical content of this object, and to see the chemical composition, and to see if also to derive other physical parameters like masses, for example, sizes, and so on, and to see if there could be, we could find any links between physical parameters to which could help, you know, that the general picture of high mass star formation is not completed, not developed even in this case. So it could help in that hot topic of astrophysics. So we used 20-meter telescope in Sweden, Onsala Observatory. So now it is equipped with a new low noise receiver from installed in 2014 year, and also has a broadband spectrum analyzer which allow to detect simultaneously a large number of molecular transition, molecular lines in the 3 mm wavelengths range. So the source list is here. So the name of the sources is actually is borrowed from a catalog of methanol masers by Yandina, but is generally it is galactic coordinates. You should actually add letter G for common notification. This association with other sources, many some of them are well-known sources, a well-known region of star formation, like for example S75, about which Igor had told in his report, CFA, also NGC 7538, and so on. And also in most of them there are bright, there are point iris sources. So these 5 sources have been observed in 2015, and in a range from 85 till 89 gigahertz, and other sources in the same range and also in the range 90 till 94 gigahertz, and together with this one in that upper range have been observed this year in 2016. This column is the distances, and I should say that we used the new distances obtained from Maser parallax measurements, and therefore for four sources of these five subsample, we used parallax estimates, and it should say that three of them, these ones, differ much from kinematic estimates used before. So in the following part of my talk, I will mainly concentrate on these five sources and their properties. So this is the table of observed molecular lines. In most of them we got maps, and what should I say? This is frequencies and energy in the temperature scale. So this is the sample of the spectrum obtained towards 121 source. This is a part of a spectral of the band in which we simultaneously observed, and you see that this is a rather rich molecular spectra. This is more common for hot cores around which is formed near in the vicinity of HIMARS stars. So all these sources are associated with HIMARS star forming regions. So now in the several next slides, I will show a couple of maps we obtained. There is also marked iris sources as white stars. If one could see this white star, which is in most cases is located in the center of emission regions, and these dashed contours in a lower row is optically thin emission. This is HCN and H13CN, HCl plus H13Cl plus, HNC HN13C, and for nitrogen bearing molecule, there is NH2D, so deuterium bearing molecule, and also N2H plus, which is marked by dashed contours. And green squares, and there are Maser source positions, and but you can read what is this. This is triangular submillimeter. So the luminosity of the iris source have been obtained by us by fitting gray body curve into iris spectra. This is not a bright source. This is about 7/700 of solar luminosity. And what should I say? That in most cases the core is more or less likely spherically symmetric. Only in NH2D molecule and also SiO there are differences from that morphology. This is two sources here. This one of these is 34.403. This is also known as infrared dark cloud. It is more or less elongated into north-south direction, but actually it is consisted of two smaller cols which we do not resolve in our observations. And here is an example of the spectrum of the maps obtained towards 37.427 source. which is in some of the line it is not really completed. So this is only in the central part. Also, this is okay. This also I should mention that here the luminosities are higher, an order of magnitude higher than the previous one, and this is also with more or less high luminosity. This source also you could see that the morphology of all molecular species I show you, except NH2D is differ. They are the same, but except NH2D, and in this case SO also, but this is very noisy man. This is the fifth source. This is extended in the northern directions, and it has the lowest luminosity obtained from iris data. Okay, so the difference between nitrogen-bearing molecules and S-bearing molecules. So we observed previously in a sample of 1,000 high mass star forming regions, mainly in a difference in N2H plus and CS line, which was explained by dissociative recombination effect in the region of enhanced ionization near luminous sources. And as for this one, from this sample, we observe such kind of differences is in distribution of different molecules. This is differences between N2H plus and H13CN. So the central source is here marked by a white star. Also, there is an ultra compact H2 region in this position. So you see that nitrogen-bearing molecules as well as NH2D molecule, they avoid the central part. But as for example, SO molecule, it is concentrated near the central source. So this is an example, the most clear example of chemical differentiation among our sources. And I should mention that this source has the highest luminosity among the sources we saw. It's about 1.5 to the 10 to the 4th power of solar luminosities. So this is an example, this is an explanation of a chemical differentiation effect for which I told you just a few minutes before. This is the most sharp differentiation we observed in W40. This is not source of the sample I am talking about, but I tell you about this. So you have seen this map Igor had shown before. In the source, the sources consisted of the clumpy ring, and here the red contours, and this is the ionized emission from the stars, which is the main driving stars of H2 optical H2 region. But it's partly optical, partly not. So in the eastern part of the ring, the SO and H13CN lines are pronounced, but in the western ones, the N2 and NH2D and H13CO plus lines, as well as HN13C, very prominent. So this is also N2H plus line is prominent in these clumps and is not found here. So this explanation is could be in general is connected with this effect of this recombination effect how to say? My lips are not pronounce this word. I'm sorry. So in the region where ionization with a high ionization. Then I will go to the part of the physical parameters. So kinetic temperature have been obtained from methyl acetylene data. You know that this is a very well known thermometer, and in dense dense regions, the rotational temperature at which populated the ladders of its spectra is close to kinetic temperature. So the values of kinetic temperatures are from about 20 to about 40 in this. Unfortunately, we found no any prominent trend in the from any prominent profiles in kinetic temperature from distance from the center. This is the maybe the hint for the decreasing of kinetic temperature with distance from the center. But you see that errors are very large. Errors came by propagation error methods from errors from the observed intensities of the components. So intensities are rather weak. Here, so from optically thin lines, we using LTE method and taking so at more or less arbitrary value of excitation temperature equal to 10. So at which most of linear molecules in most cases column densities of linear molecules have a minimum. So we calculated column densities and taking from literature the values of H2 column densities from nearly the same regions, mainly from dust observations. They have been calculated. So we calculated abundances of the molecules. So these column densities and abundances are related to the Onslow beam, about 44 arc seconds. You see that in general they vary by a factor of few from source to source. The highest abundances, molecular abundances, are in the source 34, 403, and the lowest in the 99, which is associated with iris sources with the lowest luminosity. Here is the other physical parameters are shown. This is how we process the maps. We feed into the maps convolution of two-dimensional Gaussian elliptical distribution convolved with the beam, and then we got the sizes into perpendicular direction. This is axis ratio is given here in this column, and angular size and linear size. It is a geometrical mean of these sizes in two perpendicular direction. Also, you know that you see that in most of the cases except 34. So you could see that this is the prolongation of this table, but I will tell about this using this table. So in most cases, this axis ratio is lower than 2. So this is the sizes, the emission region are more or less close to the spherical symmetric. So and in this case is the mean velocity dispersion is the mean line width. And here is a virial masses which calculated using these two parameters, sizes and mean line width or mean velocity dispersion, because these values of velocity dispersions are much higher than thermal line widths in the sources. So we also try to look at how velocity dispersions are behave with a distance from the center of the source. In that case, we calculated how the mean velocity dispersion is the dependence of mean velocity dispersion on so-called impact parameters. So we calculated average line widths for the area where intensities of in molecular line is higher than a given level. Then calculated from this from the square of this area and calculated impact parameter. And so you see that the first point on this on these plots in general is 1 point, because it is the peak intensity, and the last one is usually 10 to 15 point averaged. So you see that in four sources, this is diagram for the same source but in different lines. So it is clear that practically in all cases this average line width decrease with increasing impact parameter, which is here is we calculated power law dependencies for these scales, and it could be that it is how to say, to prove that in the center near the high mass star the dynamical activity of the gas is enhanced due to, for example, enhanced turbulence, maybe rotation or other kind of systematic motions. And you see that from the center to the periphery of the clouds, the average line width is decreased by about 1 or 1.5 kilometer per second. So the last part of my talk is concerned of profiles of these profiles which deviate from Gaussian, about what I have told you in the introduction. So this is NA-HCN and H13CN profiles taken into the position of peak intensity, and this shown by blue, and also HCO plus and H13CO plus shown by red. And you see that in some cases, so in this is in 4 cases of 5, the center of optically thin isotopic line H13CO plus and H13CN, they coincide with the absorption dip on the main isotopic line, which has a higher optical depth obviously, but the character of asymmetry of the peaks with respect to this central line is the different. So in two cases, the blue peak is higher than the red one. In two other, so the red ones are higher than blue one. And in one case we see this is rather rare fact. The spectra is more or less Gaussian. This is also examples of the spectra obtained in 6 other sources observed in 2016. So as for this case when the so-called blue asymmetry, so it is well-known fact that when the cloud is over the core is collapsing on the line of sight, there is observer and there is a cloud, and there is a temperature gradient, and you could expect existence of such kind of profiles on the lines of optically thick lines. So in the work of Myers with others, they introduced a rather simple model to calculate inward velocity. Inward velocity means the velocity on the boundary of the region inside which there is such motions. Taking the intensities of a red, blue, and intensities between them, it is possible to estimate inward velocities. And we have calculated such velocities for these two sources, where such feature in HCO plus and H13CO plus have been observed, and then calculated mass accretion rates using the radius of the region where contraction is and the inward velocity, and with the two plausible values of surrounding densities, which we don't know. We took it 10 to the 4th and 10 to the 5th power respectively, and got the values which is so in the range of the calculated values of mass accretion rates in the high mass star forming regions. So I will go to conclusion at last. So you could read what this is if you want. But I could say that for me is this work is not completed. Of course, it will be go further. At first, we could also analyze the data completely, which we got in 2016, and also I would like to analyze N to H plus data and to construct velocity gradients maps as we did before. Probably position velocity diagrams also is needed to analyze if there is a rotation in the course. So you see that these 5 cores we analyzed, they show the rather rich molecular spectrum, which is common for hot cores. And I should mention that these signatures of inward motions, they are observed in the sources with the lowest luminosities. So it could be that such signatures, blue shifted, blue skewed profiles are the signature of a high mass region, high mass star forming region at a more earlier stage of evolution than that sources which, for example, demonstrate chemical differentiation effect. So that's all. Thank you for your attention.
You
demonstrated very nice spectra, molecular spectra. I've seen two lines, no, two isomers, HCN and HNC. That's both.
You are talking about maps.
Yes, about spectra. My question is on the.
This?
No, it was at the beginning. This doesn't matter. My question is there are two isomers, HCN and HNC.
Yes.
And they looks like similar. They have similar polar dipole momentum, yeah, and they look similar. But from the point of view of astrochemistry, why these two molecules are same? In principle, one should be more stable, or how to do this? What is the difference between that? Maybe Igor knows.
No, I think that this is a question, of course. So for me, it's I think it could be the the question for
astrochemical process of how they form, yeah. So interesting.
High temperatures, the HCN is more stable.
HCN is more stable.
But here, yes, but here we see also HNC.
Probably same amount.
No, but it's a slow temperature. At low temperatures, HNC is more abundant. 2 times more abundant.
2 times more abundant.
HNC.
HCN.
HNC
more abundant.
At low temperatures. At high temperatures, HCN is more abundant.
But as for example these sources, we need to how to say it? We need more data to see how the temperature is going in this course. How it is distribution, how it is distributed. So, for example, for here, you see that this is in W40 in the western part, in the western branch of this region. This HN13CN, HN13C, which is prominent. So, but these clumps are colder. There is no evidence for this molecule.
The chemistry comes in 2 ways, at higher temperature and at lower temperature.
So it's one of those. Yes.
Is this course isolated or not?
What do you do isolated?
Any
other? No. It is of course it is not isolated at all in the universe. All of them are the parts of the large giant molecular clouds and giant complexes. So there are probably some other structure, but at the beginning I said that I concentrated only on these scales of the sub-parsec scales, and the subtitle of my talk could be what we could derive from 3 mm molecular data, and is it still interesting?
Okay.
May I put very general question, because I use in some lectures also same terms, but frankly speaking, I couldn't understand properly. When we are seeing about the concentration of molecule, the previous slide, you exactly demonstrated this. One of the maybe yes, no, you have shown it. No, this one, next to this one.
This?
No, that's not so big. This one.
This one.
Yes. When we are talking about the differentiation and concentration of molecules, that was my question that I would like to understand for myself. We observe the molecular transition, specific molecular transition, and we can observe from lower rotational level.
This is the front-end quasi-optics here shown of these 2-3 mm receivers, so it provides calibration, beam switching, and so on.
So this is the receiver installed at the antenna, at the 14-meter antenna. Well, so some auxiliary equipment, and the noise performance of this 3mm HEMT receiver. So it is the best values are about 40K here. This from about 85 to almost 200 gigahertz. Well, and this is another development. It is the 1.3 centimeter and 8mm receiver for 600 radio telescope Proton 600 in Moscow Caucasus at the Special Astrophysical Observatory. Well, I skipped this block diagrams of the receivers. Well, also some parts of this equipment. It's also this is also a cooler, showing the cooler and the part of the cooled part of the receiver. Well, what is this? I'm not sure actually. Well, so this is the development of infrared and optical, also cooling systems for the infrared and optical systems for the 6-meter telescope. We've been just recently, last week, at the Special Astrophysical Observatory. Also this cooling system has been developed here. And now the project which we maybe will be involved, it is the project which starts now. It's a 100-meter telescope which is now, which will be built in China. And it should work up to 100 gigahertz approximately. And there are, now we have a long negotiations already, several years already actually, with these Chinese people about participation in this project, development of the receivers, cooled receivers for this antenna and so on. So there is a mutual interest, but there are some details and so on. So these negotiations continue, as I say, for a long time already, and maybe they finally will lead to our participation in the development of the receivers for this telescope, which is now under construction. Actually, they want 3mm band receiver, 7mm array receiver, and some other things, dual polarization, and 2 side bands, and so on. So they have rather serious technical demands. Well, it's another it's illustration to our participation in the NATO project, and sounds interesting. So this project was actually started rather long ago, almost 10 years ago, and it continued for several years. So also we participated in cooperation with the Institute of Radioelectronic and Engineering in Moscow in this project. So they developed the SAS mixers and other things, actually so-called integrated receivers on the base of SAS mixers. So they developed special chip which includes SAS mixers, local oscillator and so on one chip. And we developed as what we can, cooling systems, some auxiliary electronics and so on for this receiver. And this is development of of the cooler for still lower temperature, 0.3 K. It is also has been made here. And the main parameters of this system you can see here. So the achieved temperature you see is about 0.3 K. Well, then there are some other developments. For example, also interesting thing, it's 10 millikelvin cryostat, still lower temperatures. and now the work is going on in cooperation. So you know that now this team has a tight cooperation with Chalmers University in Sweden, and in the Chalmers University they develop very sensitive bolometers for balloon applications and so on, for studies of the cosmic microwave ground, other things, and these bolometers need cooling for very low temperatures. And it is also this work which is shown here, so these people participate in this work in cooperation with some other. And so this team is shown here, so and this is a person from this Chalmers Technical University. Actually, he has Russian origin, Professor Leonid Kuzmin. He now works more or less permanently in this Chalmers University, but he applied for so-called mega grant here. So in our country, maybe you've heard, there is a program of so-called mega grants, which the amount is much larger than the typical grants which we can get from, for example, Russian Foundation for Basic Research, other sources and so on. So they managed to get such mega grant, and so people participate in this project under the leadership of this Professor Kuzmin, and they developed this, as I just told, very sensitive bolometers for various, mainly for space applications. Well, it's just parts of this development. So I don't know how long is this presentation. I haven't seen it. Well, so it's an example of, this is the example of the SIS mixer. The mixer itself was developed by our colleague from the Institute of Radio Electronics and Engineering, Sergei Shitov, and was manufactured here at our institute. This shows some its lenses and other parts needed for the front end. Nitrogen, liquid helium, liquid nitrogen cryostat for infrared spectrometer, for special astrophysical observatory, and it's a problem. It's recent development. It is the receiver, the amplifier, the low temperature amplifier for this 64-meter antenna in near Moscow. It is installed. This antenna is located near Moscow and is used for space communication, for far space communication, and in particular to communicate with the Mars mission. And so.
Deep space.
Yeah, deep space communication. And so our people developed these receivers in cooperation with our colleagues from Ukraine, by example. This is Alexander, how they pronounce Alexander Filipenko, who developed this, actually the chips of these amplifiers. And in this cooperation, they made a very low noise amplifier for this frequency range, about 8 gigahertz. The noise temperature was low, about 4K, even lower, and it was installed at this antenna for deep space communication. Well, and this is the receiver for investigation of atmospheric transparency at millimeter wavelengths. It was developed mainly by our well, the main designer was Vladimir Nosov from our department, and it was used to measure atmospheric transparency at various sites, including Middle Asia and North Caucasus, then some other places and so on. It is shown here. So some sites are shown here. So they even traveled to this part, eastern part of our country, in some mountain in this eastern part. It is cold pole, so-called. So here it is the temperature can drop to very low values, about -50, and even lower. And it is expected that at such low temperatures, atmospheric transparency can be very good. And so they tried to check this, but actually they made these measurements not in winter, but in summer. But in summer it was not so bad. Yes. Well, and this is the project which is made in cooperation with the Italian colleagues. They plan to launch a balloon around the North Pole. It's the Olympus project for studies of the polarization of the cosmic microwave background and also Shunyai-Zeldovich effect, for example, and so on. And so our people participate also in this project, and it should start from somewhere from Spitsbergen and other things. It's with our Italian colleague Paolo De Bernardis and Dr. Dolin, who they discuss some arrangements for this project. Well, how long is it actually? So this is illustration of for the development of this so-called cold electron bolometers for studies of the cosmic microwave background. It is work by this Professor Kuzmin, which I mentioned, and so I'll skip this. And well, this is the illustration of the project of the 70 meter radio telescope in Uzbekistan. It is this project was started many years ago. You see the year here, 1981. So the first stone was put in the basement at that time. So, and you see this monument here in memory of this. And then it was looked in this like this. So some part of was constructed of this antenna. And it is a plan how it should look. But unfortunately, when the Soviet Union crashed and funding stopped, and since that time nothing has been done. So it continues to be about the same shape as here. And there are many years there is a discussion how to revive this project. And quite recently with Boris, we discussed the development of the Russian infrastructure in astronomy, and this project was among those which were suggested to be supported. Well, we'll see, will it be supported or not. It's the decision should be from our government. So it's the project itself, as you see, 70 meter antenna which should work to 1 millimeter approximately. And this is our team which traveled there to measure atmospheric capacity. And the panels for the antenna are actually ready, and they are in rather good condition, as you can see here. These are illustrations. So it's some parts of this. Well, it seems to be them.
Any questions, anyone?
Now we are talking about the temperatures. I understand for very tiny things, and the level of millikelvins. It's now is not a record, but it is more or less.
Yeah. And we have what altitude is, by the way. There is a group here who pull some gas to very low temperatures to investigate so-called Bose condensation.
So the vector millimetron could be, in principle, provided by your team or by cooperation.
Yes, sure.
Yes,
yes. And I just, one of the goals to show these presentations to you was to our Indian colleagues was just to give the impression of our capabilities. And in case that anybody will be interested to use these capabilities, we are ready to cooperate.
To invite you to work at -50.
In India, we have just 50.
So this entry point that project, so what is the status? Is it funded and which
perhaps you noticed on the slide that there was the year 2017. Of course, now it's unrealistic totally.
But is it still on? Or?
Yes, it's still on. It's still in the program. It continues. But the launch date is now shifted approximately to 2025.
2017 was unrealistic from scratch, from the very beginning. Of course, it's a complex and very expensive project. Sure.
So is it open to foreign collaboration or is it closed?
We should contact. Sure.
The leader of this project is Professor Kardashov from the Astrospace Center in Moscow.
Yeah, still, if you need some contacts, we could provide you with. Welcome. It's not too late. In Spectrum UV, we try to cooperate with Indian colleagues, but at the moment, on the technical basis, it's too late. We try, but in science, no, they are ready. So, but in this project, millimeter, nothing is too late.
Here, conference is on electron, so you can join.
Yes, from time to time there are some meetings devoted to the neutron project.
Normally in April.
It is very distinct from scientific point of view for many people from universities. Very technically interesting and unfortunately very expensive. The next question, if you have some plans, you or maybe somebody else, to investigate, to ask